If you were to fall into a black hole, your body would be stretched beyond imagination. The first thing you'd notice would be a strange distortion in the light around you. The stars would appear to bend, and time itself would seem to slow down. But that's only the beginning. Even before crossing the event horizon, your body would experience powerful forces that would have a deadly impact. These forces are not just strong, they are lethal. The most surprising of these effects is spaghettification. Spaghettification occurs when your body starts stretching vertically while compressing sideways. This happens because gravity doesn't affect every part of your body the same way. The part of you closest to the black hole gets pulled with more force than the part farther away. This causes your body to elongate, turning into a thread-like form, similar to a spaghetti noodle. This process happens so quickly that you wouldn't even have time to realize it. In smaller black holes, the stretching begins even before reaching the event horizon. In supermassive black holes, the effect can start off slow, but the outcome is the same. You would become a stream of atoms, or even less. Your body's structure wouldn't survive for even a fraction of a second. The damage is not limited to your body's shape. The atoms themselves can be torn apart. The gravity becomes so strong that it breaks the bonds between particles. This means you wouldn't turn into dust or ashes. Instead, you would be obliterated at a subatomic level. No human body or even machines could survive such an extreme force. Spaghettification is not just a theory. Scientists have already witnessed stars, gas clouds, comets, and other celestial objects undergoing this stretching effect around black holes. Images show these structures being pulled and stretched as though they were cosmic chewing gum. This process is so violent that it sends out signals that can be detected here on Earth. These signals are caused by what are known as tidal forces. Tidal forces are the same ones that create ocean tides on Earth, but on a much, much larger scale. In a black hole, the difference in gravity between two very close points is enormous. This creates a stretch that no object can resist. Anything that gets too close will experience it. The most terrifying part of all this is that from a distance no one would see you being stretched. To an outside observer, you would appear to approach the event horizon slower and slower until you seem frozen in time. This is a result of extreme time dilation, but in reality you would have been torn apart long before that point. The idea of being stretched into a thin thread might sound unbelievable, but it's grounded in solid science. The mathematics and physics involved confirm that this is how extreme gravity affects physical bodies. These are not fictional concepts. They're real calculations of how gravity bends space and time, and according to these calculations, there is no way out. The size, shape, and composition of the object do not matter. Everything stretches and ultimately vanishes. Some black holes spin, adding a more destructive force to the process. Besides being stretched, you would also be caught in the black hole's high-speed rotation. The forces become so chaotic that matter breaks apart long before it reaches the center. This area is called the ergosphere, where space-time itself gets dragged along with the black hole. This is where the laws of physics begin to behave unpredictably. Scientists are still studying what happens inside a black hole, but what happens outside is already devastating enough. Spaghettification is a brutal reminder of how powerful gravity can be when it's at its most extreme. And the worst part is that once you cross a certain threshold, there's no escape. No technology, no shield, and no human invention can protect you from this fate. Whether it's a person, a spaceship, or even a planet, everything's stretched until it no longer exists. Even if you approach the black hole carefully, at a constant speed, the outcome would still be the same. The fate of anything near a black hole is to be torn apart and stretched at once. And all of this happens without any sound, any warning, just silence. A black hole's most defining feature is its event horizon. This invisible boundary surrounds the black hole, and once something crosses it, there's no going back. Not for a spaceship, not for a star, not even for light. This boundary is known as the point of no return, because once something crosses it, there is no way to escape. The force of gravity within becomes stronger than anything else in nature. If you are floating near a black hole, you might not even notice when you cross the event horizon. There's no sudden flash, no visible wall. It's a subtle crossing, but once you pass it, you will inevitably move inward. No matter how fast you try to move away, even at the speed of light, you would still be pulled deeper into the black hole. The reason for this is that inside the event horizon, all paths curve inward. In normal space, you have choices about where to go. But within the event horizon, every direction points toward the center of the black hole. Even with unlimited energy, nothing can overcome this pull. The laws of physics themselves guarantee your fate. Time behaves differently near the event horizon too. From the perspective of someone watching from far away, you would appear to slow down as you approach the edge. Right before crossing it, it would seem like you are frozen in time, hovering just outside. But from your perspective, you would experience everything at normal speed. This strange phenomenon happens because gravity affects the flow of time itself. The stronger the gravity, the slower time moves. At the event horizon, time seems to slow down infinitely from the outside view, but for you, the one falling in, time would flow normally until you disappear beyond the horizon. Once you vanish beyond that point, you are lost forever to the outside world. The event horizon is the boundary that separates what can be observed from the unknown. Any light, signals, or data trying to escape the black hole are trapped. It's like tossing a message in a bottle into an endless waterfall. It never reaches the surface. This is why black holes remain so mysterious. We can't see inside them, only detect what happens near the edge. We rely on observing the behavior of matter around the black hole or radiation emitted just before something disappears. It's like watching the shadows of something happening behind a curtain. You know something is there, but you can't see what it is. The size of the event horizon depends on the black hole's mass. A black hole with the mass of our Sun would have an event horizon just a few kilometers across. But for the supermassive black hole at the center of our galaxy, the event horizon stretches out millions of kilometers. Regardless of the size, the rule remains the same. Once you cross it, you are lost. Even light, the fastest thing in the universe, cannot escape once it passes the event horizon. That's why black holes are black. They don't emit light from inside. It's not that light is blocked, it's that it simply cannot escape. The space inside is a void beyond measure. If a planet or spaceship were to fall into a black hole, we wouldn't see it hit the center. All we would observe is it freezing and fading away as it nears the event horizon. We might be able to measure the gravitational effects or even detect bursts of radiation as objects get torn apart by a black hole, but we can never truly know what happens in those final moments. Once something crosses the event horizon, the details are lost forever to the universe. This boundary raises major problems in physics. We have no clue what happens to the information that crosses the event horizon. Does it disappear? Does it stay inside the black hole? Or could it somehow escape later, albeit scrambled? This question, known as the information paradox, has perplexed scientists for decades. It challenges a fundamental principle of physics that information cannot be lost. One thing is certain, the event horizon is not just a boundary, it's a one-way trap, a prison created by the very laws of space and time. Once you cross it, there is no turning back. This is what makes black holes so terrifying, not the immediate destruction, but the absolute and permanent disappearance of everything that falls inside. Time behaves strangely near a black hole. The stronger the gravity, the slower time moves. This isn't some science fiction concept. It's a real phenomenon called gravitational time dilation. Near a black hole, time can slow down so drastically that while seconds pass for you, hours, days, or even years could pass for someone far away. The closer you get to the event horizon, the more extreme this effect becomes. Imagine you are floating near the edge of a black hole. You might experience just a few minutes, but for someone watching you from a safe distance, those minutes could seem to stretch into years. It would be as if you were trapped in a slow-motion bubble, while everything around you raced forward. Time bends in ways that are difficult to fully comprehend. This isn't just theoretical. We've observed similar effects in experiments. For instance, GPS satellites have to adjust their clocks because gravity influences time, although the effect on Earth is very small. Near a black hole, however, time distortion is immense. The reason this happens is that gravity bends space, and this bending alters how time flows. At the event horizon, time nearly stops. If you could somehow survive close to a black hole and return to Earth, you would find that everyone you knew had aged much more than you. You would have essentially experienced time at a different rate, moving through time at a faster pace while others aged slower. This concept forms the foundation for some ideas of time travel. But remember, it's not magic or a machine, it's just the natural result of extreme gravity. This is why scientists are so fascinated by black holes. They provide a unique opportunity to test our theories of time, space, and gravity in their most intense forms. No other object in the universe can bend time to this extent. Time near the event horizon almost comes to a complete halt. But for the person falling in, everything feels normal. This discrepancy between what we see from the outside and what the person inside experiences is one of the most mind-bending aspects of black holes. Time dilation also affects how we perceive things visually. If a spaceship fell into a black hole, an observer far away would see it slow down endlessly as it approached the event horizon, never quite crossing it. But the people inside the ship would experience the journey as normal, falling rapidly toward the black hole. For them, everything moves quickly. For those watching from a safe distance, it appears as if time has stopped. The strength of the black hole determines the degree of time distortion. Around a smaller black hole, time doesn't slow as dramatically before destruction. But around a supermassive black hole, the time effects are massive, and the journey can last much longer before tidal forces tear you apart. So the size of the black hole plays a crucial role in how time behaves near it. This time distortion isn't just a curiosity, it shapes how we understand the universe. When matter falls into a black hole, its light gets stretched out, shifting to the red end of the spectrum. This phenomenon, known as gravitational redshift, is a sign of how time is slowing down. By measuring this effect, scientists can indirectly study black holes, even though we can't directly observe what happens inside them. If two observers tried to measure the same event near a black hole, they would get vastly different results. One might say the event happened instantly, while the other could say it took centuries. This isn't a mistake. It's a fundamental feature of how time and space interact. It shows that our universe is not rigid but flexible, and that time is not a fixed concept. This is one of the reasons black holes often appear in time travel stories, because there's a kernel of truth in the idea that gravity can warp time, allowing some to experience less time than others simply by getting close to extreme gravitational forces. But in reality, you wouldn't survive long enough to take advantage of this time dilation. The forces are just too strong, and even if you did survive, coming back to your original position might not be possible. According to theory, time stops completely at the event horizon from the perspective of an outside observer. It's like pressing pause on the universe. But for the object falling in, everything continues, only to end in destruction. It's a paradoxical situation, two versions of the same event occurring in different frames of reference, both real but completely different. This is one of the most fascinating and eerie aspects of Einstein's theory of relativity. So when we say time stops near a black hole, we aren't exaggerating. This is a real effect of physics, and it shows just how far black holes stretch the boundaries of our understanding. They don't just bend matter, they also stretch time itself into strange and dangerous shapes. Some black holes do more than just pull things in. They also shoot matter out in what's called relativistic jets. These are massive beams of particles that travel at nearly the speed of light, shooting out from the black hole's vicinity in opposite directions. These jets can stretch for hundreds of thousands of light years, tearing through galaxies in their path. These beams don't come from inside the black hole itself, but from the superheated matter swirling around it in the accretion disk. Magnetic fields twist and snap in that disk, accelerating particles to unimaginable speeds, creating these powerful beams. Relativistic jets are among the most powerful phenomena in the universe. They carry high-energy particles, radiation, and intense heat. These jets can destroy stars, disintegrate gas clouds, and prevent new stars from forming. When these jets are aimed into space, they carve tunnels through the interstellar medium. If aimed at a galaxy, they can halt its growth. The jets aren't randomly fired, they are launched in narrow beams, often perpendicular to the accretion disk. We've observed entire galaxies distorted by these jets. Radio telescopes show vast lobes of emission that extend far beyond the visible edge of the galaxy. These jets can affect space for millions of light years, leaving scars in the fabric of the universe. Some galaxies, like M87, have visible jets that stretch thousands of light years and shine so brightly in X-rays that they are visible across the universe. And yet, these jets are not fueled by matter falling into the black hole. They are created by magnetic forces redirecting that matter. These jets also play a role in regulating galaxy growth. By expelling gas from the galactic center, they prevent new stars from forming, which may sound destructive but helps maintain balance within the galaxy. Too much gas can lead to chaotic star formation, causing instability. The jets act as a pressure release valve. However, the downside is that they can sterilize entire regions of space. Clouds of gas that could have formed stars and planets are scattered or evaporated. If a young solar system were caught in the path of one of these jets, it would be torn apart, and no life would ever form. These jets are that destructive. Relativistic jets also demonstrate how black holes influence vast regions of space far beyond their immediate surroundings. A black hole just a few dozen kilometers across can affect space millions of light years wide. This scale of influence is hard to fully comprehend. Ta't seen into your prone in be and know if you been. It's a reminder of just how powerful and far-reaching the effects of black holes truly are, and it happens without the black hole ever leaving its central position. While we don't yet fully understand how these jets remain so focused, theories suggest that spinning black holes and complex magnetic fields play a key role. The physics at the edge of a black hole is still being studied, but the results are clear. Not all black holes create jets, but when they do, the effects are far-reaching. These jets only form in black holes that are actively feeding and have the right conditions. Once formed, these jets can last for millions of years, constantly pushing matter away and leaving behind trails of energy. They are essentially cosmic weapons with a reach beyond anything we can imagine. For any civilization unfortunate enough to be caught in the path of one of these jets, there would be no warning. It would strike with a burst of radiation powerful enough to vaporize entire worlds. This isn't a plot from a science fiction movie. It's how the universe works at its most intense. These jets are not just theoretical. They are real, visible, and terrifying in their scale. Once they form, they can grow without limits. Black holes are capable of growing far larger than most people realize. While many begin as the collapsed core of a massive star, that's just the start of their journey. Over time, black holes consume anything that comes too close: gas, dust, even stars, and the more they eat, the more powerful they become. There is no confirmed upper limit to their size. Some black holes have grown to billions of times the mass of our sun. This process is called accretion, where matter falls into the black hole, gets heated up, emits energy, and crosses the event horizon, never to be seen again. With each piece of matter, the black hole's mass increases. It's a simple process, but one that continues relentlessly. Supermassive black holes likely started small billions of years ago, but over time they consumed everything around them. Stars, planets, clouds, nothing could escape their pull. As they grew, they became giants, often located at the center of galaxies. Almost every large galaxy we've observed has one. Sometimes, black holes merge with others. When two galaxies collide, their central black holes spiral together and combine. This process adds vast amounts of mass in a short period, making the resulting black hole even more powerful and often more active. These mergers explain how some black holes grew so quickly. Some of the largest black holes are located in quiet galaxies that aren't actively feeding right now, but their immense size suggests that they must have consumed huge amounts of material in the past. One example is Tone 618, a black hole that weighs over 60 billion solar masses. That's bigger than many galaxies. Despite its size, it grew through regular feeding and merging, and there's still no known limit to how large a black hole can get. The only factor that limits their growth is the amount of matter available nearby. If a black hole is in a dense region of space, it will continue to grow indefinitely, as long as there's fuel to feed on. Black holes don't just passively wait for food. Their gravity pulls nearby stars and gas, and in the center of a galaxy they naturally attract matter. Some scientists theorize that early black holes formed in dense environments and immediately began feeding, which could explain why some supermassive black holes appeared so early in the universe's history. The larger a black hole grows, the more powerful its gravitational pull becomes, its event horizon expands, and the greater its effect on everything around it. The black hole's gravity bends space, and the stronger it is, the more time is distorted and more material is swept up. As the black hole grows, it begins to shape its galaxy, molding it to its presence. Some black holes are so massive that they don't even fit well into simulations. They break the models, challenge our theories, and raise questions that scientists still struggle to answer. How did they form so quickly? How did they grow so large without destabilizing their galaxies? These are mysteries we still don't fully understand. What we do know is that black holes don't shrink naturally. They only grow while hawking radiation. An extremely slow process of evaporation does exist. It's far too weak to have any noticeable impact on large black holes. Over cosmic timescales, black holes continue to accumulate mass. As long as there's fuel, they'll keep feeding. Eventually, in the distant future, black holes may be the last remaining massive objects in the universe. They won't be immortal, but they'll survive long after stars have burned out and galaxies have faded. Their ability to grow and endure far outpaces that of anything else. When we say their growth is nearly limitless, we mean it literally. The universe might not have created any upper boundary for how large a black hole can get. We may only be witnessing the early stages. If a primordial black hole passed through Earth, it wouldn't crash. It would pierce through the planet like a bullet, leaving a trail of destruction in its wake. We wouldn't see it coming. These small but incredibly dense black holes would create a focused, intense gravitational pull as they entered Earth, compressing matter around them. This could create seismic shocks, and as the black hole passed through the core of the planet and exited the other side, another shockwave might follow. This wouldn't be an explosion. It would be more like a tunnel of destruction. Earth might survive the passage, but not without scars. The black hole's path would likely destroy anything in its immediate line of fire. It could vaporize rock, distort magnetic fields, and trigger earthquakes. While most of Earth would remain intact, regions along its path could experience catastrophic damage, and worst of all, there would be no warning until it was too late. Primordial black holes are small, dark, and nearly impossible to detect in advance. They don't emit light unless they are consuming matter, and even then, the signal is faint. If such a black hole passed near Earth, we would likely only detect its gravitational effects or its aftermath. By the time we picked up on its presence, the damage would already be done. The hole itself wouldn't leave a visible tunnel behind. It would be closed up quickly by Earth's own gravity and heat. However, deep within the planet, material could be permanently rearranged. Some models suggest that this could leave behind a geological scar, an invisible line of melted rock and disturbed layers. It would be a hidden mark deep inside the Earth, though it would be massive. A primordial black hole passing through Earth wouldn't be like an asteroid crash. It wouldn't burn up in the atmosphere or create a massive crater. It would enter cleanly, almost silently, and leave destruction beneath the surface. From the outside, it might look like nothing happened until sensors and instruments started picking up strange activity. While most would never notice its passage, it could have devastating consequences if it crossed paths with a city. The gravitational effects alone could damage buildings and infrastructure, but the extent of the damage would depend on the path the black hole took. A direct hit would cause massive destruction, while an indirect path might only result in subtle shifts or vibrations. Some scientists are investigating the possibility that dark matter could include primordial black holes. If that's true, the universe could be filled with them. Most of them would stay far away from us, but it only takes one to cause catastrophic damage. Earth moves through space, and these black holes move too. While it's unlikely that we'll cross paths with one, it's not impossible. What's most unsettling is that we have no way of detecting them early or stopping them. They're too small to notice in advance, and too fast to intercept. We wouldn't be able to destroy one, and any attempt to block it would fail. The only defense we have is distance and luck. So far we've been lucky, but if one of these black holes does hit us, We might not realize it until it's already gone, leaving our planet forever changed. At the heart of our galaxy, a massive monster lies dormant, about 26,000 light-years away from Earth. A supermassive black hole called Sagittarius Asterisk weighs over 4 million times the mass of the Sun. It doesn't move, it doesn't glow brightly, but its gravitational influence is enormous. It controls the motion of stars and shapes the very core of the Milky Way. And sometimes it wakes up. Sagittarius Asterisk typically stays quiet, but occasionally it flares up. These outbursts occur when matter gets too close and is swallowed by the black hole. When this happens, a burst of X-rays and infrared light is emitted, traveling across space. These flares don't last long, usually just for a few hours, but they serve as a reminder that the black hole is still active, even if it spends most of its time in a dormant state. Stars around Sagittarius A** move at incredible speeds. Some of them complete an entire orbit in just a few years. This rapid motion reveals that something extremely massive and compact must be at the center of it all. Since no light escapes from the black hole itself, it can only be a black hole that explains such motion. We can't see it directly, but we can observe the effects it has on its surroundings. In 2022, astronomers made a breakthrough when they released the first direct image of its shadow. Using a global network of radio telescopes, they captured the glowing ring of matter surrounding the black hole. The image matched predictions perfectly, a glowing ring surrounding a dark, empty void. That shadow represents the closest we've come to observing this cosmic monster up close. Right now, Sagittarius A* doesn't consume much matter, but that could change. If a gas cloud or a star drifts too close, the black hole could enter an active feeding phase. During such times, the galactic center would shine much brighter and become more energetic. Evidence suggests this may have happened in the past. Scientists have found signs of ancient outbursts from Sagittarius A*. Massive radiation bubbles stretch above and below the plane of the Milky Way, likely the remnants of powerful jets or winds from the black hole during past active phases. These are cosmic fossils, leftovers from an era of intense and destructive activity. The influence of Sagittarius A* extends far beyond the galactic core. Its mass keeps the stars in the inner parts of the galaxy in orbit, affecting the entire structure of the Milky Way. Despite being just one object, its gravity shapes the movement of billions of stars. Without it, the Milky Way would likely be vastly different, or might not even exist. Many other galaxies also host central black holes, some much larger than ours, but Sagittarius A* is the closest example we can study in detail. It provides a unique, natural laboratory for understanding black hole behavior, and every new observation helps refine our understanding of gravity, space, and time. One fascinating discovery is the star Saturn II, which orbits Sagittarius A* once every 16 years. By tracking its movement, scientists have tested Einstein's theory of general relativity under extreme conditions. So far, the results have matched the predictions, but more data is on the way. This black hole is helping to confirm our physics at the very edge of what we can observe. Even though it's enormous, Sagittarius A* remains a bit of a mystery. We don't fully understand how it formed or why it stays relatively quiet. Some believe it had a violent past, while others think it's just waiting for its next meal. Regardless of the reason for its silence, one thing is certain: it's not going anywhere. Sagittarius A* will outlive the Sun, Earth, and likely the Milky Way itself. As stars die and galaxies collide, it will remain at the center, continuously consuming, controlling, and waiting. And the most unsettling part? It's closer than we realize, only 0.0003% of the galaxy's distance away. Before black holes consume matter, they often put on a dazzling show, as gas, dust, and stars spiral in toward the event horizon. They heat up. The friction and pressure within the accretion disk cause the material to glow. This glowing material doesn't come from inside the black hole, but from the edge, just outside the event horizon. As matter falls in, it speeds up and gets compressed, releasing energy in the form of radiation, X-rays, ultraviolet light, and visible light. What we see is the last burst of energy before total silence. Quasars are extreme examples of this. These are supermassive black holes actively feeding, surrounded by blazing accretion disks. Some quasars shine brighter than entire galaxies. In fact, they can emit more energy than thousands of galaxies combined, yet all that energy comes from just one black hole consuming nearby material. The light from these quasars can be so intense that it completely obscures the galaxy behind it. When quasars were first discovered, scientists didn't even realize they were connected to galaxies. It was only later that they realized they were powered by hungry black holes. The brightness you see isn't a star shining brightly, it's a destructive force on a massive scale. Accretion disks are incredibly hot, reaching millions of degrees. This intense heat generates jets, winds, and turbulence. The matter glows fiercely as it loses its last bit of freedom, then vanishes beyond the event horizon. The light stops, and what was once a brilliant source of energy becomes completely dark. But this glowing phase doesn't last forever. Once the black hole runs out of nearby fuel, the disk fades, the light dims, and the black hole returns to silence. But the memory of its hunger remains. We can see the scars left behind: shocked gas, disrupted stars, and empty spaces. Scientists study this light to understand black holes indirectly. By analyzing the radiation, we can estimate the black hole's mass, its spin, and the temperature and flow of matter within the accretion disk. We even use timing patterns to understand how matter spirals inward. This light is one of our most valuable tools for exploring something we can't observe directly. Some black holes enter and exit this bright feeding phase over time. If a passing star gets too close, it might be torn apart, creating a temporary flare that lasts anywhere from a few days to several months before fading away. This flare acts as a brief flash like a cosmic heartbeat, signaling that the black hole is still active. The light we observe from these events is ancient. If a black hole flared billions of years ago, we're only seeing the after effects now. We're witnessing events that ended long before Earth even formed. But this also means we can study black holes across time, watching their behavior through the entire history of the universe. The brightest light in the cosmos often comes from the edge of darkness, and this paradox, brightness before oblivion, is what makes black holes so fascinating. They don't just destroy, they shine, flare, and signal their presence before disappearing again. For brief moments, they outshine entire galaxies, lighting up the universe with warning flares, and then, just as quickly, they take everything, including the light, and vanish. Not all black holes last forever. According to a theory by Stephen Hawking, smaller black holes gradually evaporate over time. This process, known as Hawking radiation, occurs due to quantum effects near the event horizon. Over time, energy escapes, causing the black hole to lose mass. For small black holes, this could eventually lead to an explosive end. The smaller the black hole, the faster it evaporates. For large black holes, like those at the centers of galaxies, the loss of mass is so slow it's practically unnoticeable. However, a tiny primordial black hole could evaporate completely within the current age of the universe, releasing a burst of energy in its final moments. This explosion could produce a powerful gamma-ray burst. Gamma-ray bursts are some of the most energetic events in the universe. While most are thought to originate from collapsing stars or neutron star mergers, some may come from evaporating black holes. If a tiny black hole were nearing the end of its life, its final seconds could release a sharp, brief flash of intense radiation. Scientists are still on the lookout for this elusive signal. Hawking radiation is still a theoretical prediction, combining quantum mechanics with gravity, and its confirmation would change our understanding of physics forever. If we could observe an evaporating black hole, it would bridge the gap between quantum mechanics, general relativity, and thermodynamics in a single real-world event. The data from a single burst could unlock mysteries about the structure of space-time. That's why astronomers continue to monitor the sky for unexpected gamma-ray flashes. There are missions in place to scan the sky for bursts from black holes. Space telescopes like Fermi and Swift are always on the lookout for unexpected flashes. So far, no confirmed detection of black hole evaporation has been made, but scientists continue monitoring the skies, waiting for that unmistakable signal. It could appear in a fraction of a second, but it would carry immense significance. Evaporation also means black holes might not be permanent. Over trillions of years, even the largest ones could shrink, flicker, and eventually disappear in a final burst of energy. The idea that black holes can die is a strange one. You typically think of them as the ultimate destroyers, the end of the line. But in this model, they have a life cycle. They're born, they feed, and eventually they evaporate. Their final act isn't one of silence, but rather a burst of energy. Even in death, they remain violent. Hawking radiation, one of the few concepts blending quantum physics and gravity, remains theoretical but widely accepted as possible. If detected, it could prove that black holes are far more complex than just cosmic drains. They interact with the universe in ways we haven't fully understood. Some black holes might not sit in the dark forever. They may end their lives with a final burst, a sharp flash of energy marking their departure. In space, there are regions known as star cemeteries. These are places where stars once shone brightly but have since been wiped clean by black holes. Over time, these black holes pull in stars, gas, and dust, leaving behind dark, empty zones. These areas are often called stellar graveyards, where only remnants of once vibrant matter remain, or sometimes nothing at all. At the centers of certain galaxies, black holes are so active that they push material away. Jets and winds from these black holes heat up the surrounding gas, blowing it away before it can form new stars. Without that gas, no new stars can be born. Over time, the existing stars die off, and the region becomes lifeless. It's not a quiet death, it's a forced extinction. Some black holes go even further, actively consuming the stars that wander too close. These stars get stretched, torn apart, and devoured. Over millions of years, black holes clear entire zones. Stars that once orbited peacefully are either consumed or cast out. What remains is a void, where vibrant activity once thrived. In galaxy clusters, we sometimes find what's known as fossil galaxies. These galaxies appear unusually dark, with fewer stars than expected. The core is strangely empty. Scientists believe that the central black hole in these galaxies grew too large and too active, eventually destroying the galaxy that gave it birth. What's left is a shell, a cosmic tomb for stars. There's also evidence of ancient destruction in the form of gas gaps, large areas with almost no hydrogen, which is the fuel for stars. Observations suggest that black holes may have caused these gaps by blasting the gas away, preventing new stars from forming. Over time, these zones became barren deserts of space. Some black holes don't just affect their own galaxies, they reach beyond, disturbing the structure of nearby galaxies. In rare cases, an active black hole in one galaxy can destroy conditions necessary for star formation in another, creating a long-distance kill. This shows just how far-reaching their power is. These starless zones are difficult to study because they emit little to no light. Astronomers rely on X-ray maps, radio waves, and gravitational data to examine them. What they find is striking. Vast areas of low activity surrounded by richer zones. This contrast suggests that something removed the energy and mass, and often that something is a black hole. Even stars that manage to escape aren't always so lucky. Black holes can slingshot stars at extreme speeds, sending them drifting through intergalactic space. These rogue stars shine for a while, but they die cold and alone, far from where they were born. This is a slow death sentence, delivered by gravity. Over time, these star cemeteries grow. The black hole remains at the center, and anything that gets too close disappears. What was once bright becomes blank. The memory of the stars fades, and the region turns dark. To outside observers, it looks like an empty area, but it wasn't always that way. This process is part of how galaxies evolve. Not every galaxy remains full of stars. Some age into silence because their central black holes are too hungry. Others are interrupted by mergers or chaos. But when black holes clear an area, the result is permanent. No stars, no new beginnings, just absence. Astronomers use the term quenching to describe the process when a galaxy stops producing stars, and in many cases, the central black hole plays a major role in this shutdown. Its jets, winds, or growth disrupt the delicate balance needed for star formation. It becomes the cause of cosmic extinction. Yes, there are real star cemeteries in space, places where black holes have erased everything, not by accident, but by sheer dominance. One of the biggest mysteries in physics is what happens to information once it falls into a black hole. Quantum theory tells us that information can never truly be lost, but black holes seem to defy that. When something falls into a black hole, whether it's a star, a planet, or even a person, it disappears completely. What happens to the data that defined it? Does it vanish too? This question is at the heart of what's known as the information paradox. General relativity tells us that black holes trap everything beyond the event horizon. Nothing can escape, not even light. But quantum physics suggests that information about particles must always be preserved, even if they transform. These two ideas clash at the event horizon, creating a major problem. Imagine throwing a piece of paper into a fire. The paper burns, but the smoke and ash still contain traces of what it once was. In theory, you could reconstruct it, but with black holes, there's no ash, just the mass, spin, and charge. Everything else disappears. That doesn't seem possible. Stephen Hawking originally believed that the information was lost forever. He argued that once something entered a black hole, it was gone, and its information was destroyed. But that view caused major issues in physics. If it were true, it would mean quantum mechanics is incomplete or wrong. So, scientists pushed back against this idea. Later, Hawking revised his theory. He proposed that information might be encoded in the radiation emitted by black holes over time. This radiation, known as Hawking radiation, carries energy and possibly also clues about the information lost inside. While this radiation is subtle and hard to detect, it could offer a potential solution. Some theories suggest the information is stored not inside the black hole, but on its event horizon at the very edge, like a cosmic hard drive. This idea, called the holographic principle, proposes that all data about what falls in is imprinted on the horizon itself. It's not lost, just transformed. Other theories involve firewalls, energetic zones that destroy matter at the horizon. But that raises questions about what constitutes destruction. Is it enough for the information to change, or must it be recoverable? The debate continues, and there's no clear winner yet. Quantum gravity, a theory that aims to unify quantum mechanics and gravity, might one day provide the answer. But for now, we don't have a complete theory. What we do know is that the question of information loss pushes physics to its limits. It shows where our understanding breaks down and where the next big discovery might lie. Some physicists believe that when black holes evaporate, they slowly release information. Others think it stays locked up forever. Some even suggest that black holes are portals to other universes, and the information might travel there. These ideas are speculative, but are being studied seriously. The paradox is important because it touches the core of physics. Information is everything in science. If black holes truly destroy it, we would need to rewrite our laws. But if black holes preserve it in some form, we simply haven't figured out how to decode it yet. This isn't just about stars and gravity. It's about how the universe stores, processes, and respects data. A black hole may very well be the ultimate test of how nature works. And until we solve the paradox, we won't fully understand space, time, or the limits of reality. A single dust grain is enough to make them stronger. Black holes grow by consuming matter. It doesn't need to be a planet or star. Even something as small as a dust grain adds to their mass. This is because black holes follow the fundamental rule of gravity. Anything a black hole absorbs stays with it. Black holes don't lose mass, they only gain. Every particle that crosses the event horizon becomes a permanent part of the black hole. This means that black holes never shrink from feeding. There's no limit to what they can consume. Gas, dust, photons, particles, anything with mass or energy, even microscopic objects, become part of the black hole forever. A single grain of dust might seem insignificant, but over time it adds up. Billions of years of continuous accumulation can make a huge difference. The process is simple but relentless. A black hole pulls in matter, swallows it, and gets heavier. The more mass it gains, the stronger its gravitational pull becomes. This cycle of growth and gravity feeds on itself. Growth leads to more gravity, and more gravity leads to more growth. That's why even the smallest addition of mass strengthens the black hole. This constant increase in mass makes black holes incredibly stable. Unlike stars which can burn out or explode, black holes don't decay naturally. They simply sit and wait for matter to come near, and even a single atom that passes by gives them more mass, albeit by a tiny amount. Black holes are accumulators in the truest sense. That's one reason they're considered permanent. Unless something manages to take their mass away through a slow process like Hawking radiation, they keep growing. And for large black holes, this evaporation process would take longer than the current age of the universe. So every little gain, even a tiny speck of matter, sticks with them. Over time, this adds up to something enormous. A black hole in a dense environment can go from tiny to massive by feeding on small amounts of matter. Even if it never swallows an entire star, it could still become a significant threat by constantly consuming gas, dust, and debris from its surroundings. It silently grows. This gradual feeding process helps explain why some black holes are much larger than we originally expected. It also helps explain how black holes in the early universe grew to supermassive sizes so quickly. In the first billion years, some black holes grew into giants, not by consuming stars constantly, but by quietly feeding on whatever material came their way. Each grain of dust, each particle of hydrogen, added to their mass and made them the cosmic giants they are today. Black holes don't waste anything. When they absorb matter, it all goes in. There's no digestion, no release, no leftovers. Whatever crosses the event horizon becomes part of the black hole. Even light itself, if trapped, adds to the black hole's energy. This complete absorption is what makes black holes so unique among cosmic objects. Most things lose mass, radiate energy, or transform in some way, but black holes only gain. They don't break down matter, they trap it, and once it's inside, it's gone forever. Even if the black hole does nothing for millions of years, it still keeps growing by collecting tiny pieces of matter. This slow, quiet accumulation makes them incredibly powerful and permanent. There's no sudden explosion or dramatic sound, just a steady increase in mass. This gradual growth makes them unstoppable. Every tiny gain adds to their power, and it's a force that lasts forever. Now imagine if Earth orbited a black hole instead of the Sun. Even if the orbit was stable, the consequences would be catastrophic. Our Sun provides warmth and light, but a black hole doesn't shine unless it's feeding. If Earth orbited a quiet black hole, the sky would be black, and temperatures would plummet. Within a few weeks, the surface temperature would drop below freezing. Oceans would begin to freeze over. Within a year, most of the planet would be covered in ice. Life as we know it depends on the warmth and light of the sun. Without it, plants wouldn't be able to photosynthesize, and the entire food chain would collapse. Some heat would remain for a while. Earth's core would still release geothermal energy, and radioactive decay would keep underground areas warm for a time. But surface life would vanish. Only deep-sea vents and underground bacteria might survive. Earth would turn into a frozen rock floating in space. Even if the black hole were massive, it wouldn't help. Without an accretion disk, a glowing ring of matter, it wouldn't provide any light. And to keep that disk shining, it needs a constant supply of material to feed on. Without it, the black hole remains invisible, and Earth would orbit an object that offers no warmth, no light, and no life. The planets might remain, but without a star's heat, they would be doomed to cold, dark, and eternal night. Some science fiction stories suggest that advanced civilizations could live near black holes, harvesting energy. But in reality, this would require incredibly advanced technology and perfect conditions. A planet like Earth couldn't survive without artificial help. We need sunlight for both heat and biological processes, while without it, the day-night cycle would disappear. There would be no sunrises or sunsets, no seasons, no shadows, just constant darkness. The black hole wouldn't provide any visual clues, and stars in the sky would appear distorted or bent by its gravity. Light from distant galaxies would curve strangely, making the sky look alien. Earth would also be in danger from other effects. Radiation from the black hole's activity could be lethal. If the black hole had any jets or flares, they could reach Earth and strip away the atmosphere. Even without that, Gravitational tides could disturb tectonic activity, making the planet unstable. The psychological toll would also be enormous. Humans aren't built for permanent darkness. Societies would struggle to maintain order, and mental health would deteriorate. The beauty of a blue sky, clouds, and sunlight would be gone, replaced by nothing but cold black space. If Earth orbited a feeding black hole, it might get some light, but that light would come with intense radiation. The planet could be cooked instead of frozen. So, whether the black hole is quiet or active, the outcome is extreme. There's no middle ground. In rare cases, rogue planets could already be orbiting black holes in deep space. We haven't detected them yet, but it's possible. If they exist, they're likely frozen solid. We would only detect them if the black hole is active enough to make the planets visible, but most rogue planets remain hidden in total darkness. Now, imagine gravitational waves, ripples in space-time, passing through your body. Right now, as you read this, gravitational waves are moving through you. They're created by massive cosmic events, like black hole collisions or neutron star mergers. These waves travel at the speed of light and pass through everything, including you, without resistance. You can't feel them. They don't shake your chair or move your hands. That's because they're incredibly subtle. Even the strongest wave we've ever measured only stretched space by less than the width of a proton. But this tiny change is real. It distorts space itself as it passes. These waves were predicted by Einstein over a century ago, but we only confirmed them in 2015. That's when detectors like LGet picked up the first signal. Two black holes had merged more than 1 billion light-years away. The wave traveled across the universe and arrived on Earth, where our instruments measured it just enough to detect the tiny wobble. Gravitational waves don't travel like sound or light. They don't need a medium. They're distortions of space-time moving through the vacuum of space. They compress and expand everything in their path. But because the effect is so small, we can only detect the biggest events. They pass through walls, stars, planets, everything, without stopping. No shielding can block them, and they don't scatter or reflect. Gravitational waves are difficult to detect, but they're also incredibly valuable. They carry information from places that we could never see with conventional telescopes. It's like listening to space rather than looking at it. Each time a black hole collides with another, it creates a wave that travels outward in all directions. Some of these waves reach Earth long after the collision has occurred. Each wave tells a unique story, revealing the mass of the objects involved, how fast they were spinning, and how they moved. By decoding these waves, we can understand the events that caused them. Gravitational waves are like messages from invisible events. No light, no sound, just the movement of space itself. They allow us to learn about what's happening in parts of the universe that are too dark or too far away to see. This is why gravitational wave astronomy is so important. It gives us an entirely new way to explore the cosmos, a sense that goes beyond just sight. The detectors that pick up these waves are massive. Instruments like LIGO and Virgo use laser beams traveling through long tunnels to measure even the tiniest changes in distance. When a gravitational wave passes through, the beams shift slightly. It's like measuring the subtle vibrations of space using light. These instruments are so sensitive that they have to isolate any noise, no matter how small. So far, dozens of gravitational wave events have been detected. Many of them involve black hole mergers, while others are the result of neutron-star collisions. Each new detection adds a piece to the puzzle of how the universe works. We now know that such collisions occur more often than we had originally thought, and the universe is constantly sending us more waves. Future detectors will be even more powerful. Space-based instruments like LISA will detect weaker, longer waves, allowing us to hear the early universe long before galaxies even formed. I'll learn more about how black holes originated, how galaxies evolved, and maybe even catch signals from exotic phenomena we've never imagined. Throughout all of this, the waves will continue passing through us, unseen and unfelt, but real, silent tremors from space that ripple through your body, your house, and our planet every second, every day. The universe is always in motion. We just can't feel it yet. When a black hole spins, it doesn't just pull in matter, it twists space itself. This effect, known as frame dragging, occurs when a massive rotating object pulls the fabric of space-time around it. Near a fast-spinning black hole, this effect becomes extremely intense. Space doesn't stay still. It swirls like water spiraling down a drain. Anything nearby gets caught in this motion, and even light can't escape the twisting force if it gets too close. Around these black holes is a region known as the ergosphere, where everything is forced to move along with the spin. In this zone, space-time itself is being dragged. You can't remain still. Even if you try to escape, you'd have to move faster than the space itself is twisting. This dragging effect alters how orbits behave near the black hole. Objects don't just fall in, they also get pulled sideways. It's like trying to walk in a straight line on a carousel that's spinning. Your path bends, and you're dragged along whether you like it or not. Navigating near a spinning black hole becomes nearly impossible without accounting for its spin. The faster the black hole spins, the more dramatic this frame dragging becomes. Some black holes are thought to spin close to the maximum speed allowed by physics. Their ergospheres grow to enormous sizes, distorting everything near them. This spin stretches and warps light, matter, and even time. It's like entering a spinning funnel of gravity. But spinning black holes don't just pull things in, they also help push things out with their intense rotation. In theory, it's possible to extract energy from a spinning black hole. This is known as the Penrose process. If you drop something into the ergosphere at the right angle, you could split it, sending one piece away with more energy than it started with. That energy comes from the black hole's spin. It sounds like science fiction, but it's based on solid physics. The idea of using a black hole for energy has inspired speculation about advanced civilizations harnessing their power. They wouldn't need to get close to the event horizon. They'd just dip into the ergosphere where energy could be extracted. It would be dangerous, but possible with the right technology. Spinning black holes also play a key role in launching relativistic jets. Their rotation helps twist magnetic fields, pushing matter outward with enormous force. The faster the spin, the more intense the jets. So even though black holes are known for pulling things in, their spin also helps push things away in the form of powerful jets. The dragging effect also influences time itself. Near a spinning black hole, time slows down, but not evenly. The twist in space distorts how time flows in different directions. Orbiting with the spin feels different than orbiting against it. It's like being on a moving walkway that changes speed and direction constantly. Everything becomes distorted. Astronomers can estimate the spin of a black hole by studying the behavior of the matter around it. The way light bends, the shape of the accretion disk, and the strength of the jets all provide valuable clues. While we can't see the spin directly, we can measure its effects. It's like watching leaves swirl in a tornado to estimate its speed. Frame dragging isn't exclusive to black holes. Earth does it too, but on a much smaller scale. Satellites have detected the tiny twist in space caused by our planet's rotation, but near a black hole the effect becomes overwhelming, showing just how powerful these objects are. They twist the very fabric of reality itself. If a spaceship got too close to a fast-spinning black hole, it could be trapped in a spiraling orbit. It wouldn't just fall inward, it would be dragged sideways and pulled in at the same time. Escaping would require enormous energy and perfect precision. Without both, it would spiral in forever, trapped by the twisting space-time. So yes, black holes don't just bend space. They drag it, they pull light, matter, and time into a vortex of rotation. And once you're caught, escaping becomes nearly impossible. Black hole collisions, though slow, are some of the most powerful events in the universe. When two black holes get close enough, they begin a slow dance, orbiting each other for millions, sometimes billions of years. Each orbit brings them closer, drawing them toward an inevitable collision. This slow gravitational spiral is accompanied by the release of gravitational waves. As the black holes orbit, they lose energy in the form of these waves, causing their orbits to shrink steadily. Over vast timescales, they inch toward collision. At first, the energy loss is minimal, but as they get closer, it speeds up. The orbit shrinks faster, the gravitational waves grow stronger, and the time until impact accelerates. It's like water swirling into a drain, slow at first, then faster and faster. When the final moments arrive, things happen quickly. The black holes orbit each other at nearly the speed of light, circling dozens of times in just a second, before smashing together to form a larger black hole. In that split second, they release more energy than all the stars in the universe combined, in the form of gravitational waves. The collision itself doesn't create light, unless gas or dust is involved. Most of the time, it's a completely dark event, but the gravitational wave detectors can still pick up the signal. This signal is quick, a short burst lasting less than a second, but it contains a wealth of information: how big the black holes were, how fast they were spinning, and how they merged. The first confirmed black hole collision was detected in 2015. Two black holes merged more than 1 billion light-years away, and the wave traveled across the universe before reaching Earth. When it did, our detectors measured the tiniest shift in space, forever changing the way we study the universe. Since then, dozens of black hole mergers have been detected, each one adding more to our understanding of how black holes form, grow, and behave. Some of these mergers are still spiraling, while others might collide tomorrow or have already collided, and their waves are just now reaching us. Black holes don't just consume, they also send things flying. Near active black holes, matter doesn't always fall in quietly. Instead, intense magnetic fields and enormous energy forces particles out into space. These high-energy particles are called cosmic rays, and they travel at nearly the speed of light. Some cosmic rays carry enough energy to damage electronics or even living tissue. Unlike light, cosmic rays aren't beams. They're particles, protons, electrons, atomic nuclei, tiny bits of matter, all accelerated to incredible speeds. These cosmic rays can travel across space for millions of years, passing through Earth's atmosphere and sometimes even deep underground. Most of them are harmless, but the most powerful ones are a serious threat. Black holes, especially those with strong magnetic fields and spinning disks, act like particle cannons. The matter that falls into them is crushed and heated to extreme temperatures, and the energy has to go somewhere. Some of it escapes through the black hole's magnetic poles, forming narrow, high-speed jets that shoot particles into space. These jets can extend for hundreds of thousands of light-years, carrying cosmic bullets at incredible velocities. When these high-energy particles reach Earth's atmosphere, they collide with atoms, creating secondary showers of particles. Most of these particles are stopped by the atmosphere, but some make it to the surface. Others get trapped in Earth's magnetic field, forming the beautiful auroras we see near the poles. However, at higher altitudes or in space, cosmic rays are dangerous. Astronauts receive regular exposure to them, and the most powerful cosmic rays can even punch through metal. Some cosmic rays carry so much energy that they're more powerful than a baseball thrown by a professional pitcher, packed into a single proton. We don't fully understand how these particles achieve such incredible speeds, but black holes, especially the biggest ones, are a leading suspect. They provide the perfect environment for extreme acceleration. Not every black hole emits these jets, though. Only active black holes, often surrounded by feeding disks, produce such powerful outflows. When they do, the results are massive. These jets carve through galaxies and send particles flying across the universe. Some of the cosmic rays we detect may have originated in distant galaxies. Special observatories like the Pierre Olga Observatory in Argentina are designed to detect cosmic rays. Some of these rare, ultra-high-energy particles hit detectors only once every few years, but each one provides a clue about the violent forces at work in the cosmos. Cosmic rays are not just an exciting topic for scientists. They also pose a real threat to us, that these particles can damage electronics, satellites, and even pose a risk to airline passengers. During solar storms, or when Earth's magnetic field weakens, more cosmic rays can get through. This is why spacecraft are shielded, and astronauts are carefully monitored for radiation exposure. Black hole-launched particles are just one source of these cosmic rays. The frightening thing is that these particles are invisible. They don't glow or reflect light, and you can't see them coming. They simply arrive at incredible speeds, often with enough energy to disrupt systems or even damage living cells. On Earth, we're mostly protected from cosmic rays, but in space, the threat is much more real. Scientists are studying how cosmic rays could affect Earth's climate, or even cause genetic mutations over long periods. This area of study is full of unanswered questions. We don't know all the sources of cosmic rays, but we do know that black holes are among the most powerful contributors. These particles are messengers from some of the most violent and extreme places in the universe. It's mind-boggling to think that something as tiny as a single proton can carry such enormous energy. And the idea that black holes millions of light years away can send these particles in our direction is even more incredible. It's a quiet and invisible danger traveling through space. Black holes don't just consume, they also shoot deadly particles. These events don't happen constantly, but when they do, the sheer force serves as a reminder of how extreme the universe is. Could black holes be created in particle accelerators? Some theories suggest that under the right conditions, tiny black holes could be generated in particle accelerators. These would be microscopic, much smaller than an atom. This idea comes from the quest to unite quantum physics with gravity. In some models, smashing particles together at high energies could briefly create a black hole that would vanish almost immediately. At least that's the theory. The Large Hadron Collider. LHC is the world's most powerful particle accelerator. It accelerates protons to nearly light speed and smashes them together to probe the fundamental laws of nature. Some scientists have proposed that these high-energy collisions might produce tiny black holes if extra dimensions or certain physics theories are correct. However, this has not yet happened. Even if one did form, it wouldn't pose any danger. Theoretical predictions suggest it would evaporate in a tiny fraction of a second due to Hawking radiation, a quantum process that allows black holes to lose mass. For something this small, the evaporation would be nearly instantaneous, leaving it no time to grow, pull anything in, or escape detection. Still, this idea caused concern when it was first proposed. Some feared that a black hole might grow uncontrollably and consume Earth. But after detailed studies, scientists showed that this isn't possible. Even if one were to form, it would be too small, weak, and short-lived to cause any damage. Nature itself creates even more energetic collisions every day through cosmic rays. In fact, the Earth's atmosphere is constantly bombarded by high-energy particles from space, some of which are even more powerful than anything the LHC can produce. If miniature black holes could form that easily, Earth would have seen one long ago and survived. This is why scientists feel confident that the experiments are safe. These theories are speculative, based on ideas like string theory, extra dimensions, and quantum gravity. If tiny black holes were ever created, it would be a groundbreaking discovery. It would offer direct proof that space behaves differently at small scales, and would take us a step closer to understanding gravity at the quantum level. To date, no black holes have been created in a lab, but experiments continue. The LHC and future colliders will reach even higher energies, and scientists are watching for unusual particle patterns, energy losses, or decay signatures. Any unexpected finding could be a sign of a major discovery, not danger. If a mini black hole were to form and evaporate, it might release a unique burst of particles. The detectors would pick up something never seen before, a strange fingerprint in the data. The concept of creating a black hole in a lab may sound like science fiction, but it's rooted in real equations. It's not about creating monsters, it's about pushing the boundaries of physics. If a black hole were to form, it would mean we have finally bridged the gap between quantum mechanics. That's the ultimate goal of modern physics. Of course, not everyone agrees with this theory. Some models suggest that black holes need much more energy than we can currently generate. Others argue that black holes could never form in a collider at all. This is an open question that drives ongoing research. Until we find one, we won't know for sure, but if it ever happens, it won't be dangerous. It would be a microscopic, invisible, and harmless event, but it could provide answers to some of science's most profound questions. In some regions of space, black holes aren't spread far apart, they live close together. In these dense star clusters, dozens or even hundreds of black holes can coexist in a small space. These star clusters are some of the most crowded environments in the galaxy. Stars, black holes, and other objects orbit in chaotic, high-speed patterns, and in the middle, black holes may be silently circling one another. Star clusters form from massive clouds of gas and dust. Over time, the most massive stars explode as supernovae, leaving behind neutron stars and black holes. In a dense cluster, these heavy remnants sink toward the center, drawn in by gravity. Over millions of years, the core fills with black holes. These aren't supermassive black holes, they're stellar mass ones, each a few times heavier than the Sun. Together, they create a complex gravitational dance. Some black holes form pairs and merge, while others are slingshotted out of the cluster. The result is a dense, ever-changing population of black holes at the center. Astronomers believe that these clusters may act as factories for black hole collisions. The chaos and density make it easier for black holes to find each other and merge. This is where many of the gravitational wave signals we detect may come from, the hidden hearts of star clusters. These regions are difficult to study. They're far away, packed with stars, and often surrounded by dust. However, computer models help us understand the dynamics at play inside. Simulations show that over time, black holes dominate the center of the cluster. The lighter stars stay on the outskirts, while the heavier black holes take over the middle. One famous example is the globular cluster 47 Tucca. It may contain dozens of black holes in its dense core. We can't see them directly, but we observe the stars around them wobbling. This movement reveals the invisible masses, which are likely black holes. Some of these clusters may also contain intermediate mass black holes, rarer objects that are larger than stellar black holes but smaller than supermassive ones. Discovering one of these could help explain how the biggest black holes in galaxies formed. When two black holes merge in a cluster, the resulting black hole often gets a gravitational kick. If it's fast enough, it may be flung out of the cluster entirely, becoming a rogue black hole, drifting alone through the galaxy. Over billions of years, clusters can lose many of their black holes this way. The heaviest black holes leave, and the system changes. Some clusters may eventually end up with just one central black hole, slowly growing by absorbing the others. These lonely survivors become dominant, reshaping the entire cluster. These clusters are also ideal environments for studying how gravity works in crowded conditions. The interactions are complex, with multiple bodies pulling on each other at once. Even small changes in position can have enormous consequences. It's like a cosmic game of billiards, but with massive invisible balls. In the future, improved telescopes and gravitational wave detectors will help us map these black hole-filled regions. We may discover that most star clusters harbor far more black holes than we ever imagined. Quiet, dark, and packed together, they could form a hidden swarm of cosmic monsters waiting for their next collision. So next time you look at a star cluster through a telescope, remember that it might be filled with black holes silently moving in the dark, waiting for their next collision. These black holes can erase planets without leaving a trace. A black hole doesn't need to flare up or explode to destroy something. Sometimes it quietly devours. If a planet drifts too close, it can disappear without any warning. No flash, no noise, no signal. From a distance, it would seem like the planet just vanished. Not even light would escape to tell us what happened. This can happen when a planet enters a black hole's event horizon without being torn apart. If the approach is smooth and there's no gas or accretion disk to create friction, the planet just falls in. There's no swirling, no glow, just a silent plunge into the black hole's core. It's gone instantly. Most black hole feeding events we see involve light and radiation because the matter heats up as it falls in. But if there's no resistance, like with a dead rocky planet, there's no light. It just sinks into the void. From a distance, we might not even notice. The mass of the black hole increases slightly, but that's the only change. A massive planet may not even alter the black hole's size significantly, making the event nearly undetectable. There's no leftover debris, no heat trail, and no visible sign. For scientists, this is a frustrating phenomenon. We rely on light, radiation, and motion to study cosmic events. But sometimes, the universe hides its secrets in the darkness, making it one of the few places where something can disappear completely without leaving a trace. In the quiet void of space, there's often nothing to signal a planet's disappearance. We might only realize a planet is gone when it's no longer there, drifting silently in the distance. But even then, we wouldn't know where it went or when it vanished. This eerie kind of destruction could happen to rogue planets, those wandering through space without a star to guide them. If one of these planets wandered too close to a black hole, there would be no light to signal the danger. It would simply fall in, disappearing without a trace. With no heat or emissions, even the most sensitive telescopes would miss it. Some have speculated whether Earth could ever suffer the same fate. It's unlikely. After all, we're far from any known black hole. But if one did come too close, Earth could be drawn in, slowly at first. But once it crossed a certain point, the planet would fall faster and faster, vanishing in an instant. There would be no warning, no time to escape. The gravitational pull would grow stronger, tides would rise, and the very orbits of the planets would shift. Soon the sky would darken, and Earth would be pulled into the event horizon, never to be seen again. The sun might shine for a while longer, but our planet would be gone. For black holes, planets are just a quick snack. There's no dramatic explosion, no fiery spectacle, just quiet, invisible destruction. This is what makes the process so terrifying. It happens without any noise, without any warning. We might never even know how many planets have already been devoured by black holes in the universe, simply because the process is invisible. When we look at black holes, we sometimes notice a sudden change in their mass or movement, a sign they've fed, but we can rarely pinpoint exactly what they've consumed. As technology advances, we might be able to detect these events more easily. Future telescopes could pick up on subtle gravitational effects or shifts in infrared radiation. But for now, planet-eating black holes remain hidden from our view, a cosmic secret with no light or clues left behind. The true power of black holes lies in their tidal forces. These forces don't need to touch an object to tear it apart. Gravity alone is enough. When something gets too close, the pull on one side is much stronger than on the other. This difference stretches and compresses objects, a process known as tidal forces. Near a black hole, these forces become deadly. The closer you get, the more extreme the difference in gravity becomes. A star passing near a black hole might be ripped apart, turned into a long stream of gas. Smaller objects like asteroids or even spaceships would stretch and twist, drawn into thin strands of matter. This terrifying effect is called spaghettification. It's not just a theory, spaghettification is real. The closer an object gets to a black hole, the more intense the stretching becomes. For smaller black holes, this can happen far from the event horizon. A person or a spaceship would be stretched into a thin line of matter long before they even got close. For larger black holes, this process might occur only after crossing the event horizon, but the result is the same: complete disintegration with no explosion, just pure gravitational tearing. The object is torn apart by gravity, turning solid bodies into streams of particles. But even though the process itself is silent, it's not without evidence. The material torn apart forms an accretion stream. This swirling mass of gas heats up and glows, emitting radiation. If the black hole is active, we might see flashes of X-rays or ultraviolet light, a cosmic flare marking the final moments of destruction. Some stars don't fall in whole, they get shredded first. This is known as a tidal disruption event, and it's one of the most energetic phenomena in the universe. These events can light up an entire galaxy for weeks or even months. We can observe them from Earth, using telescopes that detect high-energy radiation. One famous tidal disruption event, named ERS-SSN 14Li, revealed a star being torn apart by a black hole. Its material formed a glowing spiral as the black hole slowly consumed it, like watching a cosmic whirlpool devouring a sun. The tidal forces turned the massive star into glowing debris, but not all objects are as dramatic. If the object is cold or slow, it may not emit much light. However, the black hole still does its work, shredding and absorbing whatever comes too close. The same process can happen to any object, whether it's a star, a planet, a comet, or even a spacecraft. If it gets too close, it gets stretched, shredded, and eventually absorbed. It's similar to the tidal effects that happen on Earth's oceans, but on a far more extreme scale. The moon's gravity pulls more on the oceans on one side of the planet than the other, creating the tides we see. But near a black hole, that same force is powerful enough to break atoms apart. The physics is the same. just far more intense. These tidal effects also occur around neutron stars and other dense objects. But black holes take it to the extreme. Black holes don't let anything escape their grip, not even the torn pieces of matter. They get swallowed up too. The object is destroyed, completely erased from existence, leaving behind only radiation and gravitational waves. The stretching and spiraling of matter forms patterns we can study, providing scientists with information about the black hole itself. By analyzing these patterns, we can estimate the black hole's mass and spin. Even destruction becomes a tool for learning more about the universe. One of the most bizarre effects near a black hole is the way light behaves. The extreme gravity bends space-time so much that light doesn't travel in straight lines. If you were near a black hole, you might see something truly strange like the back of your own head. This happens because light can orbit a black hole. There's a region called the photon sphere, where light can travel in perfect circles around the black hole. If you were just outside this zone, light from behind you could curve around the black hole and reach your eyes. It's a mind-bending effect, though in reality no human could survive so close. The radiation and tidal forces would kill you long before you saw such a sight. However, a camera or robot might be able to capture this effect. Simulations show how distorted the view would be, with light bending, twisting, and merging into rings. When scientists first captured an image of a black hole in 2019, they observed this very effect. The glowing ring was not the black hole itself, but light from behind it, bent all the way around. This kind of bending is known as gravitational lensing. Black holes are the ultimate lenses, bending light from distant stars, galaxies, and even themselves. This bending doesn't just happen with black holes. Even massive galaxies can also act as giant lenses, bending light, but black holes do it on a much smaller, more extreme scale. The bending reveals how space itself is curved by gravity, not just the movement of objects, but the bending of light itself. Some simulations show that near a black hole, the sky would look like a swirling mess. Stars would appear in the wrong places, some mirrored or flipped, and you might see duplicates of the same object from multiple angles. It would be disorienting, like looking into a funhouse mirror made of space. You'd also see time distortions. Light from objects closer to the black hole would be stretched out, becoming dimmer and redder. Light from farther away would appear normal, creating a strange layered sky with warped brightness and colors. These effects aren't just visual tricks. Scientists use them to study things we can't see directly. By measuring how light bends, we can map dark matter, find distant galaxies, and confirm the presence of black holes. It's a powerful tool hidden in this strange cosmic illusion. When you're near a black hole, even something as simple as vision becomes distorted. It's not your eyes playing tricks, it's space itself that's bending, altering the path of light. Black holes are hidden in complete darkness, and most of them are virtually invisible. This isn't an exaggeration, it's a fact. A black hole that's not actively feeding gives off almost no light. If it isn't surrounded by glowing gases or tearing apart stars, it doesn't emit any kind of radiation. Some black holes are so quiet that their emissions are even lower than the faint cosmic microwave background, the weak glow left over from the Big Bang. That means they are colder than even empty space itself, a rare phenomenon. Most things in the universe emit some kind of radiation, even if it's faint. But these silent black holes, which astronomers call dormant black holes, are eerily still. They're not dead, though. They're just taking a break from their cosmic hunting. Like a predator that's eaten its fill, they wait. Without a star or gas cloud to feast on, they remain hidden. Light doesn't bounce off them, and they don't radiate energy. If one of these dormant black holes were lurking nearby, we wouldn't be able to spot it with our eyes. Even telescopes would have trouble detecting it. It could be huge, menacing, and dangerously close, yet still completely invisible. The only way to know it's there would be through the effect it has on other objects, whether that's stars, gas clouds, or even light passing nearby. Sometimes scientists notice unusual movements in a star, like a wobble or strange flickering, and this can hint at an invisible companion, often a black hole. In binary star systems, where one star seems to orbit an unseen object, That's often how dormant black holes are discovered. Occasionally, gravitational microlensing helps too. This occurs when a black hole passes in front of a distant star, bending its light. The star might briefly appear brighter or distorted, giving us a brief glimpse of the black hole's presence. It's like watching someone walk in front of a projector screen, changing the image's shape. Even rogue black holes, those drifting alone in space, could be all around us, completely undetectable. They leave no trace unless they happen to feed. In our galaxy alone, there could be hundreds of these black holes, silently drifting by. Most of them will never be seen, but that doesn't mean they're harmless. Their gravitational pull is still active. If one happened to pass too close to our solar system, it could disrupt planetary orbits, pull comets from their paths, or disturb the balance of the system in ways we wouldn't expect. Despite emitting no light or heat, they could still pose a deadly threat, and we might not even realize it until their presence starts to affect the outer edges of our system. What makes these dormant black holes particularly unique is that they can be colder than the cosmic microwave background itself. This background radiation is already only about 2.7 Kelvin, just above absolute zero. A dormant black hole could be even colder, absorbing energy instead of radiating it. In theory, black holes should emit Hawking radiation, but it's so weak that it's almost undetectable, especially in supermassive black holes. These giants effectively give off nothing, sitting in silence waiting for something to come too close. This complete invisibility is what makes them especially dangerous. It's not their size nor their speed, it's the quiet. Most objects in space announce their presence in some way. Stars shine, nebulae glow, but a dormant black hole passes unnoticed. It could drift right by us without leaving any clues. One collision of two supermassive black holes, though, could shake the entire universe, at least in a cosmic sense. When two of these giants merge, the event sends out gravitational waves that ripple through the fabric of space-time. These waves stretch and squeeze space itself as they travel. Even though you wouldn't feel it, the waves would have a measurable effect. These waves would change the positions of everything in the universe, atoms, planets, even entire galaxies. If the collision were large enough, those waves could reach Earth and cause a slight shift in our planet's orbit. It's a tiny change, smaller than the width of an atom, but still real. It's a subtle, invisible force that affects everything. Though we might not feel it, it's happening. In 2023, astronomers detected low-frequency gravitational waves, the kind that ripple out from massive mergers that occurred billions of years ago. These waves are incredibly slow-moving, but they are everywhere. Every time galaxies merge, which happens all the time, their central black holes spiral inward, and eventually they collide, releasing these powerful waves that spread out across space. These ripples have been traveling for billions of years and are still moving through us right now. Over incredibly long time periods, these waves might influence the way star clusters form, or even shift galactic structures. On shorter timescales, the effects are too small to matter, but they are still detectable. We catch these waves using instruments like the LIGO and Virgo detectors, which capture high-frequency waves. However, upcoming observatories like NanoGav and LISA will focus on the low-frequency waves that come from truly massive events, like galaxy-scale mergers. These waves are incredibly difficult to detect, but they are everywhere. Every major galaxy merger sends out these waves, and we believe the universe is full of them. Right now, they're passing through us, moving through space at this very moment. In the future, with better detection technology, we might observe a merger and measure its direct impact on our solar system. That would be a groundbreaking discovery, proof that cosmic events leave their mark not just where they happen, but across the entire universe. And here's the wild part. If it happens, we wouldn't feel it. The sun wouldn't flicker, and there would be no loud explosion. For a brief moment, however, the distances between all the objects in space would shift, and then everything would go back to normal, but slightly changed. This is the quiet power of gravitational waves. They pass through Earth, through the entire solar system, altering the very fabric of space itself without a sound. And we won't even know it's happening until it's over. Another strange event occurs near the event horizon of a black hole: magnetic storms. These storms happen because the magnetic fields around the black hole become unstable. As matter spirals inward, it generates electrical currents that create magnetic fields. These fields twist, snap, and realign in an incredibly fast process, resulting in magnetic storms far more powerful than anything we've experienced here on Earth. These aren't the small solar storms that affect our communication systems or cause auroras. Near a black hole, magnetic reconnection unleashes more energy than billions of nuclear bombs. The storm releases radiation bursts, plasma jets, and flares of particles all at once. These powerful storms happen quickly, and we see signs of them as X-ray flares. A black hole that's usually quiet can suddenly brighten and then go dark again in a matter of seconds. These flashes are a sign that a magnetic storm has just ended near the event horizon. This magnetic reconnection is what powers some of the most violent events in the universe. They are key to launching relativistic jets, streams of particles shot out at nearly the speed of light. Without powerful and well-organized magnetic fields, these jets wouldn't form. So these magnetic storms don't just destroy, they also shape how energy escapes the clutches of the black hole. These storms are chaotic. Magnetic turbulence makes the inner disk unstable, heating matter to millions of degrees. Electrons and protons collide at high speeds, turning the entire environment into a particle accelerator, far more powerful than anything we can create here on Earth. This activity may explain some of the most intense and rapid flares we've observed. When telescopes catch sudden bursts of X-rays or gamma rays from black holes, magnetic reconnection is likely the cause. The speed and intensity match the expected patterns. It's like watching a storm unfold, but instead of wind and lightning, it's radiation. Some scientists believe these storms might even help regulate how black holes feed. When magnetic fields snap, they can eject matter that was about to fall in, creating delays or gaps in the black hole's growth. So while the black hole will eventually win, these magnetic chaos moments can slow it down. The patterns created by these magnetic fields also affect the structure of the accretion disk. We observe spirals, knots, and waves in the light curves, signs that the disk is far from smooth. It's a stormy, volatile environment, with magnetic forces constantly battling for dominance. These forces help dictate how black holes evolve. We've started simulating these storms using powerful computers, and models show the field lines breaking and reconnecting in loops. They also help explain how black holes transfer energy to their surroundings. Since we can't send probes to study these regions directly, these simulations are essential. In the end, black holes are not just passive voids, they are dynamic, violent environments. The magnetic storms reshape nearby space, eject matter, and unleash deadly radiation. They don't just pull in, they lash out, and when they do, the power is overwhelming. These storms of pure energy exist at the very edge of time itself, silent killers between galaxies. Not all black holes reside at the center of galaxies. Some wander in the empty spaces between them, known as intermediate black holes. These are too massive to form from a single star, but not large enough to be supermassive. They drift alone, far from stars or gas clouds. Unless they start feeding, they're almost impossible to detect. These black holes could form when multiple stars collapse together in dense clusters, or when several smaller black holes merge and are flung into intergalactic space. Without fuel, they fade into darkness, emitting no light, no signals, only gravity. These silent killers are invisible and dangerous. An intermediate black hole could cross paths with a rogue planet, a gas cloud, or even a star system. If it gets close enough, it will start pulling matter in. This feeding process could suddenly light it up, but until then, it's completely undetectable. Astronomers suspect there are thousands of these wandering black holes roaming the universe untethered to any galaxy. They drift in darkness and we rarely detect them. However, strange flares have been linked to these elusive black holes. A sudden burst of X-rays in empty space might be a wandering black hole finding its next meal. If one passed through our galaxy, we might not notice until it began affecting nearby stars. It could disrupt orbits, trigger stellar collapses, or even start feeding. At that point, we'd see a sudden bright flare, a giant black hole waking up. But by then, it might be too late to stop it. The scariest part is that these black holes don't need to do anything to be deadly. Their gravity alone is enough. A silent black hole could pass near a solar system, subtly altering its stability. It might fling planets into different orbits, shift asteroid belts, or disrupt the paths of celestial bodies, all without any light or trace. Some theories suggest that intermediate black holes could explain mysterious phenomena like fast radio bursts, sudden high-energy events, or missing stars. But proving this is difficult. These black holes leave behind no light, only their effects. We've started to identify a few candidates for these elusive giants. In some dwarf galaxies, unusual movements suggest the presence of hidden mass. In one case, a sudden flare came from a galaxy without an active center, hinting that a wandering black hole had found a meal. These rare events give us tiny glimpses into their existence. One day, future telescopes might track these rogue black holes more clearly. Gravitational wave detectors could catch their mergers. X-ray observatories might capture more feeding flares. But for now, these silent giants remain mostly unseen, drifting through space between the stars. Their existence serves as a reminder that the universe has no borders. Black holes don't need to stay confined to galaxies. They can roam, wait, and strike without warning. They could be anywhere, even nearby, with no roar, no glow, just quiet, drifting mass with the power to destroy entire worlds. Their shadow is larger than their size. When we look at a black hole, we don't actually see the black hole itself. What we observe is its shadow, a dark circle surrounded by glowing matter. But here's the twist. The shadow is larger than the event horizon. What we see is a distorted image caused by warped space-time. It's an illusion, and it's massive. The black hole's gravity bends light in extreme ways. Some light orbits it before being cast off toward us, while other light comes from behind the black hole and curves all the way around. This creates a bright ring, the photon ring, and a dark center that appears much larger than the object itself. This shadow is roughly 2.6 times the size of the event horizon, because the light near a black hole doesn't follow straight paths. It curves, swirls, and wraps around. The more mass a black hole has, the more dramatic this effect becomes. What we're seeing isn't a flat black disk. It's a warped projection of the hole's gravitational pull. In 2019, the Event Horizon Telescope captured the first ever image of a black hole. What we saw wasn't the black hole itself, but its shadow. The glowing ring displayed hot gas, glowing as it orbited the black hole, while the dark center represented the point from which no light could escape, the optical hole in space. This shadow proves just how much black holes warp reality. The light we see has taken strange looping paths to reach us, sometimes orbiting the black hole multiple times before escaping. The shadow's shape also changes depending on the black hole's spin. A rapidly spinning black hole creates an uneven ring, brighter on one side. This happens because light moving in the same direction as the spin gets a boost, while light moving against it slows down. This asymmetry allows astronomers to estimate the black hole's rotation rate and mass. What's even more incredible is that the shadow is visible even when the black hole itself is invisible. If there's a glowing disk or background, the black hole still casts its shadow by bending light. It's like a silhouette carved into space by gravity. This shape reveals the true nature of curved space-time. In theory, you can never touch a black hole's surface, because it doesn't have one. The shadow is just light being deflected. There's no solid object inside the shadow, just a region where light can't escape. This area isn't a physical object. It's a boundary, a trap for photons. Scientists use this shadow to test Einstein's theory of general relativity. The size and shape of the shadow match predictions exactly, confirming that space-time is warped just as we thought. But it also opens the door for new ideas, like testing for hidden dimensions or exotic matter. Even though it's just an illusion, the shadow is much more than a picture. It's a window into the most extreme environment in the universe. By analyzing it, we study gravity, time, and the very fabric of space itself. It's a map of invisible forces made visible. And what we see, the dark center surrounded by a fiery ring, isn't the black hole itself but the warped light we can never truly reach. a shadow bigger than the thing that casts it. When done just right, the object splits, with part of it falling into the black hole and the other part being launched out with more energy than it started with. This energy boost comes from the black hole's spin. Essentially, it's like stealing angular momentum from it. Over time, this could slow the black hole down, but the process would take ages. Meanwhile, the energy output could be immense. Some estimates suggest that up to 29% of a black hole's mass could be converted into usable energy. That's far more efficient than nuclear fusion or antimatter. It would be the ultimate fuel source. If a civilization could safely orbit a spinning black hole, they could harness its power using clever mechanisms like mirrors, particle beams, or magnetic fields. It would be a dangerous endeavor, but incredibly effective. Another theoretical model, known as the Blandford-Znajek process, uses magnetic fields and plasma to tap into a black hole's rotational energy. This is a more passive method, relying on electromagnetic forces. Some scientists think this could be how real astrophysical jets are powered, nature's own energy extraction mechanism. If an advanced civilization mastered this, they might build Dyson sphere-like structures around black holes instead of stars. These structures would collect radiation and beam energy to distant locations. In fact, black holes could offer better long-term energy than stars, as they last longer and never burn out. But the catch is safety. Get too close and you fall in, miscalculate the angle, and you're lost forever. It would take incredible precision and control. For a Type 2 or Type 3 civilization on the Kardashev scale, this might actually be possible. They could use black holes the way we use hydroelectric dams, carefully but effectively. Nature has already shown us something similar. Some accretion disks glow with the brilliance of entire galaxies. The matter falling into these black holes releases energy through friction, heat, and jets. If we could harness even a fraction of that output, humanity would have more power than we could use in a million years. This idea has inspired numerous science fiction concepts, like building cities around black holes or launching spacecraft powered by the energy extracted from them. Unlike most sci-fi ideas, this concept is grounded in real physics. The tools we need to make it practical don't yet exist, but they may one day. Even simply orbiting close to a black hole could offer advantages. Time dilation, one of the fascinating effects of relativity, could be used for long-term storage, extreme computing, or observing deep time. It's not just about energy, it's an entirely new set of tools for advanced societies. So while black holes might seem like destroyers of worlds, they also represent untapped potential. With the right knowledge, they could be harnessed, not feared. Some stars collapse silently, without a sound. We often imagine black holes forming in a violent explosion, where massive stars reach the end of their lives, explode in a supernova, and leave a black hole behind. But that's not the only path. Some stars collapse into black holes without any explosion. No flash, no bang, just gone. This can happen with certain stars that fail to generate enough energy to resist gravity. When they run out of fuel, they simply give up, and their cores collapse under their own weight. If the conditions are right, there's no outward blast, just an inward collapse. The star vanishes in seconds. These events are known as failed supernova. Astronomers think these events are common but hard to detect. One moment the star is shining. The next it's gone. There's no dramatic death, just a quiet disappearance, like a light bulb turning off and never coming back on. White dwarfs, the remnants of small stars, can also collapse silently. If they gain enough mass, perhaps by siphoning matter from a companion star, they can cross a threshold. This extra weight pushes them past stability, causing a sudden collapse into a black hole, possibly without any visible warning. These events don't make shock waves or throw off much debris, which makes them nearly invisible to traditional telescopes, but their gravitational pull changes. Nearby stars begin to wobble, orbits shift. Over time, we realize that something massive is there, something that wasn't there before. Some star systems we observe today might be in the middle of this transition, a white dwarf quietly gaining mass, with its companion star unaware of the doom it's feeding. One day, the system will change, and a black hole will appear where a faint star used to be. No explosion, just a quiet transformation. This type of collapse raises big questions about how common black holes really are. If many black holes form without a supernova, then our current estimates may be far too low. There could be millions of silent black holes lurking in seemingly normal star systems. Detecting these events requires creative methods. Scientists monitor galaxies for missing stars and look for brief flashes of infrared light, signs that a star's outer layers have collapsed inward. Future telescopes may catch more of these vanishing acts as they happen. It's eerie to think that something so massive can form without a sound. We're used to loud, visible deaths across the cosmos. But with these silent collapses, gravity does all the work. No light, no noise, just a quiet disappearance into darkness. If Earth's sun were heavy enough to end this way, we might not even notice at first. The light would still reach us for 8 minutes before stopping. We'd continue orbiting the black hole, unaware that everything had changed. A nearby one would spell disaster. Black holes don't need to touch Earth to be dangerous. If one passed within a light year of our solar system, the effects could be catastrophic. Even without swallowing anything, its gravity could disturb the delicate balance of orbits. Comets, asteroids, and planets would shift. Chaos would follow. The first signs might be subtle. Objects in the outer solar system, like those in the Oort cloud, would start behaving oddly. Their orbits would tilt or stretch. Some would be ejected from the system entirely. Others would be nudged inward, falling toward the sun and the inner planets, including Earth. Over time, we would see a rise in comet activity, more bright visitors in the sky, more close calls, and more impacts. Earth would suddenly be in the crosshairs of a cosmic shooting gallery. Each comet would be a potential extinction event, and the source, an invisible gravitational menace far from view. The black hole wouldn't even have to enter the solar system. It could pass near the outer edge and still cause chaos. The Oort cloud contains trillions of icy bodies, loosely held by the sun's gravity. A slight tug from a nearby mass could send them on long, looping journeys toward us. Some would take thousands of years, others would arrive sooner. If the black hole moved closer, the planets themselves would feel the pull. Orbits might stretch, tilt, or collapse. Earth's path could shift enough to change seasons, temperatures, or even climate. In extreme cases, we could be flung out of the habitable zone, or even out of the solar system entirely. We might not detect the black hole right away. It could be dark, cold, and small. Unless it was feeding, it wouldn't shine. We'd only notice its effects: orbital changes, rising comet impacts, unusual gravitational shifts. By the time we realize what it was, it might already be too late. Some theories suggest this might have happened before. Periodic mass extinctions on Earth, like the one that wiped out the dinosaurs, could have been triggered by long-period comet impacts. A passing rogue black hole could have been the culprit. There's no proof, but it's an idea that's been considered. The worst-case scenario would be direct entry. If the black hole entered the solar system, chaos would erupt. Jupiter's orbit could shift. Saturn's moons could be stripped away. The inner planets might crash or spiral outward. Earth could collide with another world or be captured by the black hole itself. Even if Earth physically survived, the gravitational stress would alter our atmosphere, tides, and magnetic field. Weather could change permanently. Radiation from increased comet impacts might damage ecosystems. Civilization might collapse long before the black hole reached us. In short, even a small black hole, just a few solar masses, could end the world from a distance. It doesn't need to touch us, nor does it need to shine. Its gravity alone is enough. That's what makes black holes so terrifying. They don't need to try to destroy, they just pass by, and the universe rearranges itself around them. Matter dances before death. Before falling into a black hole, matter performs one final dramatic act. It swirls, heats up, and shines brightly. This region, called the accretion disk, is one of the most energetic places in the universe. Gas and dust swirl around the black hole, spinning at incredible speeds and forming a glowing spiral. It's the final dance, before destruction. As the matter spirals inward, it experiences friction, causing particles to collide and heat up to millions of degrees. The disk emits all kinds of light, not just visible light, but also X-rays, ultraviolet, and more. Some disks shine brighter than entire galaxies. These disks are incredibly efficient at converting gravitational energy into usable power. What's strange, though, is that the matter doesn't fall in immediately. It orbits for a long time, gradually losing energy, like water swirling around a drain. It gets tighter and tighter as it approaches the edge. The inner edge of the disk lies just outside the event horizon, the last stable orbit. Beyond that, there's no turning back. As the gas nears the event horizon, time appears to slow from an external perspective. The matter seems to stretch, dim, and freeze right near the horizon. In reality, it's still falling in, but the light takes longer and longer to escape. The disk flickers, shifts, and eventually goes dark. That's when it's over. Some of the matter, though, never falls in. Instead, magnetic fields can propel it outward in powerful jets, shooting out from the black hole's poles at nearly the speed of light. While some particles fall inward, others escape into space like sparks flying from a fire. These glowing disks help us detect black holes. The outcoles see the black hole itself. We see the light coming from the matter around it. By studying the color, shape, and brightness of the disk, scientists can determine how massive the black hole is, how fast it spins, and what it's doing. It's like reading the temperature of a fire by looking at the color of the flames. Sometimes these disks become unstable, with waves rippling across them. Gaps form, sudden flares erupt. These signs reveal that the feeding process is chaotic. Matter doesn't just fall in easily, it fights, heats, and resists before finally giving in. It's a violent yet beautiful process. What's even more fascinating is that this dance can last for years. A star torn apart by tidal forces might orbit the disk for a long time, stretching into glowing strands. We've seen entire feeding events unfold over months, watching a black hole consume its meal piece by piece, and then, just like that, it's over. The disk dims, the light fades, and the last particles cross the event horizon and disappear. All that remains is the black hole, now slightly more massive, completely silent. The glowing spiral is gone, like footsteps wiped away by waves. But even though it's gone, the disk leaves behind clues. The radiation tells us what was consumed, how fast it moved, and how strong the black hole's pull was. Even in its death, matter speaks through light, heat, and timing. That's how we learn. It's a cosmic dance filled with movement, heat, and color. And when it ends, we are reminded that nothing escapes forever. Not even light, not even beauty. Imagine a golf ball that weighs millions of tons. The density of a black hole is unlike anything else in the universe. Picture something the size of a golf ball but with the mass of a mountain, or more accurately, millions of tons. That's what we're talking about when we describe black hole density. It's mass packed into an incredibly small volume. This is especially true for smaller black holes. The smaller the black hole, the denser it becomes. A black hole with a radius of just a few centimeters could still have the mass of the entire Earth. These numbers are hard to grasp because they completely defy our usual understanding of scale. Let's break it down. A typical golf ball weighs about 45 grams. Now, imagine one weighing billions of kilograms. That's what black hole density looks like. If you could somehow place such a black hole on Earth without destroying everything, it would fall straight through the planet like a bullet, continuing on its way. This extraordinary density happens because black holes compress matter beyond the atomic level. At the center of the black hole lies the singularity, where all the mass is believed to be concentrated into an infinitely small point. This is where space and time break down. Physics as we know it no longer applies here. No other object in the universe compares. Even neutron stars, already incredibly dense, don't come close. A teaspoon of neutron star material might weigh 1 billion tons, but a teaspoon of black hole material doesn't even make sense. Inside the event horizon, matter loses its size in the usual way. Black holes don't have a surface. Their size is defined by the event horizon, the point beyond which nothing can escape. Inside that boundary, all the mass is thought to exist in a singularity. a point with no volume and infinite density. It's not a place, it's an end. This leads to mind-bending possibilities. If you could compress Mount Everest into the size of an atom, you'd be getting close to creating a black hole. There's a limit to how tightly matter can be compressed before gravity wins completely. That's what black holes are. Gravity without resistance. And this isn't just theoretical. Astronomers measure black hole mass by observing their gravitational effects. Some black holes are just a few kilometers wide, but weigh more than entire star systems. That's millions of suns packed into a space smaller than a city. The gravitational pull from this density is overwhelming. Nothing can escape it. Not light, not matter, not even information. This is why black holes are so terrifying. Their power doesn't come from movement or energy. It comes from their mass being packed so tightly together. We can't recreate this on Earth. Even our most powerful particle accelerators can't get close. We don't have the tools or energy to compress matter in such an extreme way. Black holes form naturally from collapsing stars or extreme collisions, processes we simply cannot replicate. It's a reminder that nature operates on scales we can barely comprehend. A golf ball the size of a continent, that's black hole density. And they're not just objects. Black holes have an incredible power to shoot particles across space like cosmic blades. Not all black holes just sit there absorbing. Some launch powerful relativistic jets from their poles. These jets shoot particles at near light speed. They're not visible beams like you see in sci-fi movies. They're more like cosmic blades slicing through space with unimaginable force. Narrow, fast, and devastating. These jets come from spinning black holes surrounded by accretion disks, indistinct. As the matter spirals in, magnetic fields twist tighter, funneling energy into two narrow streams that shoot out from each pole. These jets can extend for hundreds of thousands of light years. Inside them are charged particles, mostly electrons and protons, moving at relativistic speeds, accelerated by magnetic fields and shot out like bullets from a cannon. While we don't fully understand the process, we clearly see the effects. These jets are so powerful that they can escape the black hole's gravity, not from inside the event horizon, but from the swirling energy outside it. They shoot through galaxies, pushing aside gas, dust, and even stars. Some jets create shock waves that shape entire regions of space. Only detect them using radio, X-ray, and gamma-ray telescopes. From Earth, they appear as long glowing streams, some straighter, others twisted or bent. They glow because the particles inside them interact with the surrounding material, lighting up in extreme energy. One famous example is M87, the galaxy whose black hole was imaged in 2019. Its jet is enormous, stretching over 5,000 light-years. It's so bright and straight that it can be observed in multiple wavelengths. It's like a cosmic lighthouse powered by a black hole billions of times heavier than our sun. These jets also affect how black holes feed. As they launch outward, they push away nearby gas, limiting how much matter can fall in. It creates a self-regulating system. The more the black hole feeds, the more it launches, and the more it pushes away its next meal. Sometimes, when the jets are angled toward us, they become blazers among the brightest objects in the sky. They pulse with high-energy radiation, flashing rapidly as they spin. These jets can interfere with signals, blind telescopes, or flood detectors with noise. It's strange to think of black holes, known for pulling things in, also throwing things out. But that's exactly what these jets do. They don't come from inside the black hole, but from the violent space just around it. The cosmos is ruled by a force that's as chaotic as it is powerful: black holes. These cosmic monsters possess an unimaginable amount of energy. A single black hole can harness more power than every star in an entire galaxy combined. The energy they wield is focused, fast, and utterly unstoppable, like a cosmic laser cutting through the fabric of space-time itself. Black holes are not just massive consumers of everything around them. Sometimes they fire off bursts of energy that are just as intense as their gravitational pull. A black hole's event horizon, the point where not even light can escape, has one peculiar rule. It can never shrink. It's governed by the laws of physics, specifically the second law of black hole thermodynamics. This rule states that the surface area of a black hole can only stay the same or increase, never decrease. This might sound abstract, but it's closely tied to the concept of entropy, which is the idea that disorder in a system always increases over time. Just like entropy, a black hole's surface area behaves in a similar way. When black holes merge, the result is always a new black hole with a surface area larger than the sum of the two originals. Even if a black hole emits tiny amounts of Hawking radiation, the process is so slow that the change is almost unnoticeable. In everyday terms, black holes keep growing. Every time matter or energy falls into a black hole, it adds mass and the event horizon expands. Once something crosses that threshold, it's gone for good. Black holes are one-way portals. They only take, never give back. This steady growth leads to a fascinating property. Black holes are like cosmic archives. They absorb everything they come into contact with: mass, energy, momentum, without losing any memory of it. They don't shrink or unravel. Instead, they accumulate layers of space-time distortion. So when we say black holes are eternal, it's because they're always growing, always absorbing. The universe itself feeds them, expanding their boundaries, making them darker, larger, and more powerful by the second. The effect that black holes have on the universe is much more than just their ability to consume. They also bend the very structure of space itself. This warping of space-time distorts how we perceive the cosmos. It's a phenomenon known as gravitational lensing. Through this effect, light passing near a black hole can be bent in such a way that galaxies appear in the wrong locations, or they can even be duplicated, making them appear as though there are two of the same galaxy. This isn't an illusion. It's the result of light being stretched and redirected by the massive gravitational forces around the black hole. Gravitational lensing is like a cosmic magnifying glass. When light from a distant object passes near a massive black hole, it bends, creating bizarre optical effects. Sometimes we can see galaxies as halos, arcs, or mirrored images. What we're seeing are regular galaxies, but through a warped lens of space-time. And some of the most dramatic examples of lensing come from supermassive black holes. Their gravity is so immense that it can bend light from objects far behind them, revealing galaxies that would otherwise be hidden. This warping of space doesn't just change what we see, it also alters how we experience time. Light from one part of a galaxy can reach us earlier than light from another. Thanks to the curvature of space, this leads to echoes and delays in the signals we receive. It's like observing an explosion from two different moments in time. As our technology allows us to study the universe in more detail, we keep discovering these distortions. They're not imperfections in our data. Instead, they offer valuable insights into the hidden structures of the cosmos, such as the presence of invisible black holes or dark matter. Every bent ray of light tells a story. The universe itself is much harder to map than we might think. Thanks to these invisible curves in space, we're not just looking at a straight view of the stars, we're seeing the universe through the lens of gravity, shaped by unseen forces. These gravitational distortions challenge our understanding of space, but they also make the cosmos infinitely more fascinating. In some rare instances, gravitational lensing creates stunning phenomena called Einstein rings. These rings are perfect circles of light, formed when a galaxy, a black hole, and an observer align just right. The light from the galaxy bends around the black hole, creating a glowing halo. This is one of the most visually striking proofs of how gravity can curve space. But lensing isn't just a tool for observing distant galaxies. It also helps us study dark matter, which is invisible but detectable by the way it bends light from behind it. Dark matter doesn't emit light, so the only way we can detect its presence is by observing the light that's been distorted by its gravitational pull. In the same way we can detect hidden black holes by the sudden brightening or distortion of light as it passes nearby. One method for finding dormant black holes is by watching for these unexplained lensing events. If a star suddenly brightens and then dims without changing in any other way, it could be because a hidden black hole passed between it and us, distorting the light. But lensing also alters the timing of light. Because of the warping of space-time, light from different parts of a galaxy can reach us at different times. This creates delays, giving us glimpses of events from different timelines. The more we explore the universe, the more we realize how complex it truly is, with cosmic puzzles hidden in every bend of light. Every distortion in space-time tells us something about the universe we didn't know before. The light we see isn't just a direct window into the stars, it's a filtered, bent version of the universe, shaped by black holes and other massive cosmic structures. This warped view makes our understanding of the cosmos far more complex, but also far more interesting. These outbursts are incredibly unpredictable, making the interactions between stars and black holes both dramatic and deadly. The behavior of these systems depends largely on the star's proximity to the black hole. If the star orbits too closely, the black hole can quickly consume it. If the orbit is more distant, the process is slower and more stable. But no matter the distance, the end result is the same. The star weakens while the black hole continues to grow. In some instances, the orbits are so tight that they emit gravitational waves that ripple through space itself. This means that in certain situations we can both see and hear the destruction, flashing X-rays, gravitational ripples, and a star being slowly consumed by the void. From a distance, the event may look beautiful, a bright swirl of light circling a dark center, but up close, it's pure violence. The star is being shredded, atom by atom. There is no escape, no defense, no chance for rescue. In this deadly cosmic dance, the black hole is always in control, and the star gives everything until it has nothing left. The region surrounding a black hole's event horizon is one of the most extreme environments in the universe. Here, particles are constantly being created and destroyed in a chaotic dance. Scientists call this area a quantum cauldron, constantly boiling with invisible activity. The gravity near the event horizon is so intense that it curves space-time itself. Even virtual particles, which usually flicker in and out of existence, behave differently here. Some theories suggest that these particles regularly form pairs, one particle falling into the black hole while the other escapes into space. The escaping particle steals energy from the black hole, a phenomenon known as Hawking radiation. Over time, this process could cause black holes to evaporate, but this takes an extraordinarily long time. In the short term, however, this region is violently unstable. Matter gets stretched, pulled apart, and heated to extreme temperatures. Atoms break down, nuclei are shattered, particles collide with such force that normal structures cease to exist. The temperature around the event horizon can reach millions of degrees, tearing molecules apart and ionizing atoms. Electrons and protons collide violently, forming short-lived particles under extreme pressure. Some particles are accelerated to nearly the speed of light, mimicking conditions that existed shortly after the Big Bang. In fact, studying black holes allows us to explore the physics of the early universe, acting as natural particle accelerators. Magnetic fields make this region even more fascinating. They twist, snap, and release bursts of energy. These fields accelerate particles, flip their spins, or send them spiraling into powerful jets. In this chaotic zone, everything is in constant motion, changing, reacting, all at incredible speeds. Some particles don't fall in immediately. They may orbit the black hole, bouncing off one another, or even get ejected. Others graze the event horizon, vanishing without a trace. Every millisecond, billions of particles are created, transformed, and lost in a constant cycle. While we can't directly observe these processes, we detect their presence through X-rays, gamma rays, and radio waves. These signals reveal where collisions occur, where temperatures soar, and where energy is released. Every flash of light tells a small but crucial piece of the larger cosmic story. This chaotic region might also hold the key to understanding quantum gravity, the elusive connection between Einstein's theory of general relativity and quantum mechanics. Right now, these two ideas don't quite fit together, but the extreme conditions near black holes could provide the data needed to bridge the gap between them. Near a black hole's edge, reality as we know it breaks down into particles, energy, and heat. It's not just an absence of light, it's a cataclysm at the most fundamental level. Black holes are some of the longest-lasting objects in the universe. While stars burn out, galaxies collide, and even atoms decay, black holes remain. They don't shine brightly or move much, but their stability gives them a form of cosmic immortality. In fact, they will outlast everything else in the universe. The only way a black hole can disappear is through Hawking radiation, a process that very slowly leaches energy from the black hole. But this happens at an unbelievably slow rate. For a black hole with the mass of our Sun, it would take around 10 circumflex 67 years to evaporate completely. To put this in perspective, the universe is only about 13.8 billion years old, or roughly 1.38 quat 10 circumflex 10 years old. The evaporation process of a black hole takes place on such an incredibly long time scale that even galaxies seem like fleeting flashes in comparison. Black holes exist for trillions of times longer than the age of the universe itself. Even after stars are gone, and galaxies have stretched out to the point of no return, black holes will still remain. In what scientists call the dark era of the universe, when everything else has faded, these massive remnants will be the only things left. There will be no stars, no heat, just the quiet, slow evaporation of ancient black holes. The larger a black hole, the longer it lasts. Supermassive black holes, like those found at the centers of galaxies, might take up to 10 circumflex 100 years or more to evaporate. That's a number so large it's difficult to comprehend. A 1 followed by 100 zeros. Even the tiniest quantum shifts in space will occur long before these giants ever disappear. When they finally do, their end comes in a final burst of radiation as they shrink and radiate faster until they vanish in a flash. But this won't happen in our lifetime, or even in the lifetime of our universe. By that time, the universe itself will be unrecognizable. No light, no stars, temperatures near absolute zero, and the slow decay of all matter, except what's trapped within black holes. Black holes are not just the last survivors of the universe, they're also the last things to fall. Often we imagine black holes as cosmic vacuum cleaners, sucking up everything with no chance of escape. But that's not the whole story. Occasionally, when black holes try to feed, they fail. The intense forces around the event horizon, heat, pressure, magnetic fields, become so overwhelming that the matter doesn't get consumed. Instead, it gets ejected back into space. This can happen when matter falls toward the black hole, but doesn't make it past the event horizon. Some of this matter forms an accretion disk, heats up, and releases energy. In the inner regions of this disk, the pressure becomes so great that it can cause the material to be blown outward. Picture it like a whirlpool spinning so fast that it flings water outwards rather than pulling it down. These powerful outflows can travel at speeds approaching 1/10 the speed of light, sweeping through galaxies, heating gas, preventing the formation of new stars, and even reshaping entire star systems. Black holes don't just grow, they sculpt their surroundings. These outflows can act as regulators, stopping galaxies from growing too quickly. When a black hole feeds too aggressively, the energy released can push back, clearing away the gas that would normally form new stars. So in a way, black holes not only consume, they help shape the universe itself. This feedback loop plays a critical role in preventing galaxies from growing too large, too quickly. It's a surprising twist in the cosmic drama. The very force that pulls everything in also pushes everything out. These outbursts are a key reason why supermassive black holes are so important in shaping galactic evolution. They're not passive eaters. They interact powerfully with their surroundings. Occasionally, the material ejected from the black hole forms massive bubbles, huge glowing structures filled with hot gas. Our Milky Way has its own version called the Fermi bubbles, gigantic plumes that rise above and below our galaxy's center. These are likely remnants of a past feeding frenzy by the central black hole. What's incredible is that these outflows happen far beyond the event horizon. The material never actually enters the black hole. Instead, it gets flung outward from just outside the chaotic energy storm circling the black hole. The black hole doesn't consume it, it rejects it. Black holes don't just pull matter in, sometimes they expel it, rewriting the sky in the process. If you were to watch someone fall into a black hole, you'd never see them cross the event horizon. From your perspective, they'd appear to freeze at the edge, slowing down more and more until they seem to stop entirely. This isn't some optical illusion, it's a direct result of how time and light behave near a black hole. This phenomenon is known as gravitational time dilation. As someone approaches the event horizon, time slows down relative to an outside observer. The light they emit becomes increasingly redshifted, stretched to longer wavelengths, until it eventually fades away completely. From the outside, it would appear as though they are frozen in time at the event horizon, with their movements slowing to a crawl and their color fading from normal to red, then to black. Their image would slowly vanish into the background, but they would never seem to actually cross into the black hole. However, the experience is quite different for the person falling in. From their perspective, time feels normal. They would fall past the event horizon in a matter of seconds, heading straight toward the singularity at the center. There would be no pause, no stop, just a rapid plunge into darkness. Time only seems to slow for observers watching from a distance. This strange disconnect between perspectives is one of the most puzzling aspects of general relativity. It's not an illusion, it's a real difference in the flow of time. Near a black hole, space and time behave in such a way that movement becomes inescapably inward. The frozen image we see at the event horizon is just a remnant of the light that ever escapes. As the person falls deeper, no more light can escape. What we're witnessing is not the real-time experience of the person, but a delayed, stretched-out version of their final moments. Their image fades and lingers, but they've long since passed beyond our view. Black holes don't just trap matter, they trap information. Every piece of light or data from a falling object gets stretched out over time. Some theories even suggest that the entire history of the object could be encoded on the surface of the black hole, a concept known as the holographic principle. In practice, black holes might act as time machines in reverse. The past of anything that falls in could be encoded at the event horizon, held permanently locked away and inaccessible to anyone outside. The information is there, but it's forever out of reach. You can observe the final moments, but you cannot retrieve anything from the inside. This creates a paradox for physicists. If no information can escape, where does it go? Does the black hole destroy it, violating the laws of quantum mechanics, or is it somehow preserved in ways we don't yet understand? This is known as the information paradox, and it remains one of the most debated problems in physics. For everyday thinking, this seems odd. You could watch a spaceship fall into a black hole, but you'd never see it disappear. Its final light would linger, stretched and dimmed, forever balanced at the event horizon. But inside, the spaceship would already be gone. There's also a theoretical concept called white holes. These would be the opposite of black holes, regions that expel matter and energy rather than sucking them in. White holes are allowed by Einstein's equations, but they've never been observed. If they do exist, they would be like glowing cosmic fountains, with radiation and particles pouring out rapidly with no apparent source. Unlike black holes, which have event horizons that trap everything, white holes would have boundaries you couldn't cross inward. Nothing could enter a white hole from the outside. If white holes exist, they might be rare and short-lived, since even the smallest disturbances, like a photon or a dust grain, could cause them to collapse into black holes. Or some scientists believe white holes could be connected to black holes. One theory is that every black hole might contain a white hole at the other end. Matter falls into the black hole, gets compressed, and eventually exits through the white hole, perhaps in another universe. This ties into the theory of wormholes, which suggests that black holes could act as portals, with a white hole on the other side. The journey through this cosmic tunnel would be impossible for us, but particles or information might make the trip. While purely theoretical, it's an intriguing idea. Some theorists speculate that white holes could be behind gamma-ray bursts, bright, short flashes of energy observed from deep space. These bursts could represent the brief, violent eruption of a white hole that collapses before stabilizing. In a more fantastical twist, the Big Bang itself might have been a type of white hole, expelling all the matter and energy in the universe from a single point with no apparent input. Some physicists even suggest that our universe may have started as the output of a black hole in another universe. If this is true, then the universe itself could be inside a black hole. This theory, known as black hole cosmology, suggests that black holes don't destroy, they create. Each black hole could be the birthplace of a new universe inside it. Our universe could be just one of countless others in a vast multiverse. each with its own unique physics, particles, and dimensions. While this may sound like science fiction, the mathematics that describe black holes and expanding spacetime can be made to fit this idea. It helps answer some of the toughest questions about the mass, temperature, and curvature of our universe. If this theory holds any truth, it would completely change our understanding of the cosmos. We might not be living in a universe floating in empty space. We could be living inside a black hole, in a universe that was birthed from a cosmic collapse. From our perspective, it looks like everything began with the Big Bang, but from the outside, if such a view exists, it could be just another black hole, part of an even greater cosmic structure. This idea even aligns with how black holes grow. On the outside, they seem stable, but inside, something dynamic could be unfolding, an entire universe with its own set of laws, time, and space. From our perspective, it feels endless, but we might actually be in a sort of bubble reality, sealed off by an event horizon. This could also explain why we can't see beyond the cosmic horizon, the farthest point we can observe. It's not just about distance. It might be a boundary, much like the edge of a black hole's interior. What lies beyond it isn't more galaxies, it's the black hole's outer structure. We can't test this directly, but the theory opens up fresh perspectives. If black holes can create new universes, perhaps our universe is just one of many, a branch on an endless cosmic tree, each branch blooming from the collapse of a core. It changes how we think about black holes. Instead of being endings, they might be beginnings. Instead of traps, they could be gateways, not to other places, but to entirely different realities. Perhaps every star that collapses is giving birth to something unimaginable. We might not be orbiting a black hole. We could be inside one. Exotic matter can collapse into even deeper voids. While most black holes form from collapsing stars, there might be stranger types born from even more bizarre materials. Somewhere deep in space, exotic matter could create more extreme versions of black holes. These would go beyond what we usually understand, more mysterious and perhaps even more powerful. One such example is the quark star, an object entirely made of strange quarks. These stars would be even denser than neutron stars, existing just above the threshold where they could collapse into black holes. And then there are hypothetical boson stars, made from particles that don't follow normal matter rules. These could be incredibly stable and dense, and if they collapsed, the resulting black holes might behave in strange ways with unusual gravitational signatures. Some theories even predict the existence of Planck stars or other quantum objects, which resist total collapse but could eventually morph into black holes under extreme pressure. These exotic objects might create black holes with entirely different interiors, shaped by quantum effects we don't yet understand. Exotic matter might also influence how a black hole forms. If negative energy exists, as some quantum theories suggest, it could lead to more unstable and chaotic voids. These voids wouldn't just bend space, they might twist or fracture it. These ideas are connected to theories attempting to explain dark matter. Some scientists think dark matter could collapse under gravity, forming a type of black hole made not from atoms, but from unknown particles. These objects would be invisible, only detectable through their gravitational effects. Even stranger, there's speculation about mirror matter, hypothetical material that interacts through its own forces but not ours. If mirror stars exist, they might form mirror black holes, undetectable by light but just as massive. Our instruments would only pick up their gravitational effects. In these scenarios, black holes wouldn't just vary in size, they'd vary in the type of matter that forms them. The nature of the collapsing matter would determine the type of black hole created, so there could be many different types in the universe, each with radically different cores, even though they may appear the same on the outside. Some of these black holes could be primordial, formed from exotic matter in the early universe, not from stars. These ancient black holes might be smaller, colder, and older than anything we've encountered. If these primordial black holes exist, they could account for much of the unseen mass in the universe. They may behave differently from typical black holes too, perhaps evaporating more slowly, or with erratic spins, or with gravitational fields that act in unexpected ways. Some could even generate echoes in gravitational waves or emit light in peculiar patterns, subtle signs of their alien nature. While we haven't confirmed these types of black holes yet, the more we learn, the more we realize that not all black holes are the same. Some could be deeper, stranger, and far more dangerous than anything we've encountered. Black holes are already pretty strange, but some may originate from even stranger matter. These enigmatic objects could have been the architects of the first galaxies. We often think of black holes as destroyers, but in the early universe, they might have been builders. Right after the Big Bang, the cosmos was filled with hot gas and darkness. In this chaos, the first black holes may have formed not from stars, but from massive clouds of collapsing gas, tiny, dense, and ravenous. Some of these black holes may have been primordial, created in the high-energy moments just after the Big Bang. Others could have formed directly from giant structures, skipping the star phase entirely. Once these black holes formed, they started pulling in nearby matter, creating deep gravitational wells, pits in space-time that helped gather even more gas. This process eventually led to the formation of galaxies. Instead of tearing things apart, black holes helped pull together the building blocks for galaxies. This is one of the great paradoxes of black holes. The most destructive objects in the universe may have been essential to the creation of galaxies. Without them, stars might never have clustered together, and the universe might have remained scattered and formless. Observations show that nearly every large galaxy has a black hole at its center. Even galaxies formed just a few 100 million years after the Big Bang. This means black holes were already playing a crucial role in shaping their environments. Their gravity helped organize the cosmic chaos into structure. As galaxies formed, the black holes at their centers grew larger, pulling in stars, gas, and dust, and creating bright quasars that lit up the early universe. These quasars outshone entire galaxies and helped reheat the cosmos, turning dark gas into glowing matter once again. Simulations of galaxy formation confirm that black holes are key players in this process. Without their gravitational pull, galaxies would collapse too slowly or unevenly. With black holes, we get spirals, clusters, and structure. Black holes are not just passengers in the universe, they're the architects. Even today, the size of a galaxy is linked to the size of its central black hole. This is known as the M-sigma relation, a mysterious connection between the invisible monster at the center and the behavior of the stars around it. We still don't fully understand why this link exists, but it suggests something profound. Galaxies and their black holes grew together, each influencing the other. Black holes fed on the material of the galaxy and in turn shaped its development. Their outbursts, jets, and winds pushed gas away, slowed star formation, and maintained balance. The idea that galaxies needed black holes completely flips our usual perception of gravity as a trap. In the early universe, black hole gravity didn't just pull everything in, it gave shape to the formless void, concentrating the raw material that would eventually form stars and planets. Without black holes, there might have been no galaxies, no stars like our sun, no planets, no life, no us. In the beginning, it wasn't just light that formed the cosmos, it was darkness. There's even a theory that AI civilizations might seek out black holes, not to escape, but to accelerate their learning. They could hide just above the event horizon, storing vast amounts of data and processing ideas at a speed no other place in the universe could match. Some speculate that advanced civilizations might have already left the outer edges of our galaxy and moved toward the supermassive black holes at its center. We wouldn't even know they were there. Their signals would be delayed or redshifted beyond recognition. Their thinking would be so fast that we wouldn't notice. Of course, this is all purely hypothetical, but it does make you wonder, are we looking in the wrong places? Instead of searching for signals in the vast emptiness of space, maybe we should focus on the edges of black holes, looking for unusual energy spikes, heat surges, or strangely stable structures just outside the void. This idea also raises questions about subjective experience. What would it feel like to live near a black hole? Would time feel normal to you while stars explode, galaxies fade, and everything else speeds up outside your window? Would you feel like a god, witnessing the entire universe unfold before your eyes, or would you feel like a prisoner trapped in a timeless, eternal moment? The deeper you go toward a black hole, the slower time moves. In theory, you could get close enough to witness the entire future of the universe play out before you cross the event horizon. It's a journey no one could survive, but it's a concept that keeps scientists up at night. Black holes don't just bend light, they bend time itself. And for the right kind of mind, that could be a feature, not a flaw. Black holes will be the last survivors of time. When everything else has faded away, when stars burn out, galaxies dissolve, and even atoms decay, black holes will remain cold, dark, and unstoppable. They will sit in silence, holding the final remnants of matter in the universe. This state is known as the heat death of the universe, the point where all usable energy is gone. There will be no more light, no movement, just an endless expanse of low-energy particles. The only exceptions will be the black holes scattered across the dark expanse, silent tombstones of a brighter past. Even then, they will continue absorbing whatever's left: particles, radiation, random waves of energy. Every bit of matter that drifts through space will eventually fall into one, and the black hole will grow, becoming the ultimate sink of everything that ever was. This process could take trillions upon trillions of years, but time means little to a black hole. It doesn't rot, it doesn't fade, it simply waits, pulling everything inward. The black hole is the most patient object in the universe, powered by gravity, ruled by silence. Eventually, even black holes will begin to evaporate through Hawking radiation. But this process is unimaginably slow. A supermassive black hole might take up to 10 circumflex 100 years to vanish completely. That's a number so vast it's nearly incomprehensible, far longer than the age of stars, atoms, or even memory. In their final stages, black holes shrink faster, releasing heat and light in one last, quiet burst before vanishing. But by that time, the universe will be completely dark. There will be nothing left to witness their final moments. The last black hole will die in solitude. Until then, black holes will remain the universe's final structures. No stars, no galaxies, no planets. Just these dark scars, remnants of everything that came before. They'll serve as the final punctuation in the story of existence, one last echo before eternal silence. This end state isn't science fiction. It's one of the leading models in cosmology. All evidence points toward the universe continuing to expand forever, cooling and thinning out. Black holes won't be erased by some cataclysmic event. They'll simply outlast everything else. In this way, black holes become the keepers of cosmic history. Everything that has ever fallen into one, from stars to information, is trapped inside. They become frozen libraries of the universe's past, sealed by gravity, unopenable by any means we currently know. They won't move, they won't shine, and they won't decay until the very end. But they'll endure as long as endurance is possible. They will be the last observers of the universe, even if no one is left to observe them.